Hello. Good evening, everyone.
Good evening.
Hello.
Hello, good evening.
Yeah, yeah. I'm audible, right?
Yes, sir.
Okay. So I think we have completed week 3 and 4, right? In the previous revision session, we have uh, completed this 2 weeks, week 3 and 4, and I think we are remaining with week 1 and 2. Is that correct?
Yes. Yes.
Yes, sir. But your voice is coming very low, sir.
Yeah, just okay. I'll raise my voice maybe when I start the session properly. Is it coming fine? Uh,
Yes, yes.
Yes, sir.
Yeah,
it's not
yeah,
that
better
loud,
than
right?
previous.
Yeah. Okay. Just give me a minute. We'll start. Okay. Okay. My screen is visible, right? Yeah. Okay. So I'll not in this session. What we can do is we may focus on the important concepts from week 1 and 2, right? I'll not go into very much details what happened in the initial slides of week 1 and 2, right? So where Professor Arun talks about uh, why this representation learning is important with respect to principal component analysis. Is that correct? Uh, by now, so I'm hoping that all of you have gone through week 1 and 2 content properly, right? So wherever there is any doubt, right, you just stop me there and you can ask me the question. So from these weeks, you may expect the questions which are theoretical as well as the numerical, right? So that front you should be aware of, like how to solve the questions, uh, numerical as well as theoretical. So I think theoretical people will be better, but sometimes whenever the numericals come in, they might lose marks, right? So I hope you have solved few previous year questions as well. If you have any doubts in previous year questions, you can ask me. We can solve it together here.
Sir,
Is
I
that
have
okay?
one request. So, at the
Yes.
end, if possible, can you please give one example of EM algorithm? Actually, I am having trouble in this.
In EM algorithm. Okay.
Yes, yes, yes. One example, not the theory part, the
Uh,
example.
numerical you're saying, or
Numerical, yes.
okay, fine. Okay, so let's start with this first. Somebody has raised the hand, or no, this revision session is for week 1 and 2. Okay. Is 2, which is for weeks 1 and 2. Okay. So first week is related to finding out the principal components, right? Or this is called as PCA. PCA is principal component analysis. Uh, so this is one of the unsupervised learning techniques, right? What is the difference between supervised and unsupervised? I think we have talked it previously as well, but can you just tell me what is it quickly?
Unsupervised has no labels, so no training data is there for unsupervised.
No, training data will be there, but we will not have the corresponding labels, right? So we have the features, but we do not have the labels to that. Like we do not know what is our end goal is, right? In supervised case, we know what to predict, right, or what to infer from the training data. Here, that is not the case. So we need to find out the patterns, right? Patterns in the data. That is what, like based on the features which are available to me. So the data set in this case will be looking like what? Uh, we have x1. X1 is what? What is
Data,
x1 here? Huh?
data point.
Data point, and it may contain, so each of xi is of let's say d-dimensional data, right? Right. So when I say each of this is d-dimensional data means it is a vector, right? X1, x2, x3, x like to xn, right? So I is equal to 1 to n. That means we have n training examples, fine? We have n data points in the data set, and each of this data is of d-dimensional. Okay, so that means how many features we are having in this case? Features.
D number feature.
D are the features, and n are what? Data points, right?
Data point.
So
Data.
here D means it's a number of features, right? Number of features, and or you can say number of dimensions, and you have n equals to number of data points. Is that okay? I think see the distinction between this you should be very clear with, right? You know what is so when I say there is a person and I'm taking the two features of it, like for example height and weight, okay, and I have such n person. So I have taken the data of height and weight of n people or n persons, right? In that case, how many features are there? Two features, right?
10.
Right. No, two features and n data points, right? So let's say for each of which, if I say that, let's say I have x1, which is equals to uh, maybe I'll find it out height and weight. So I'll just denote it by h1 w1. X2 will be the height of the second person and the weight of the second person. X3 will be height of the third person and weight of the third person, right? And similarly I have n such persons, right? So I have recorded uh, n persons height and weight, and that is n is what? Number of data points or number of examples. And how many? So in this case, let's say in this example, x1 equals to h1 w1, x2 equals to h2 w2, x3 equal to h3 w3. How many dimensional data set is this?
3 dimension.
Two dimensional.
Why three?
Two
Two
dimensional.
dimension.
Two dimensional.
Two
H1 and
dimension.
so how will I plot this h1, or maybe not h1, let's say height on this. So let's say it is h, and suppose w is my weight. So if I see for this, let's say this is one data point, right? So this is x1. There is another data point which is suppose x2. There is another data point which is x3, like this, right? So this is how I should be plotting these data points, right? And then we will see that what are the what is the underlying structure of this data set. Fine. So or we wanted to find out the patterns of this data set, because I do not know what to predict for, right? I just have collected height and weight, but I do not know what I need to predict it from here, right? So that is what the case is. Maybe if I know also, then also I can use this PCA technique, because PCA is used to what? PCA technique is the unsupervised learning technique, but what it does basically,
Dimension reduction.
yeah, so if your data uh, lies into a lower dimension subspace, I will be able to represent the same data set using the lower dimensions, right? Like let's say if I can, let's say in this case, if I can draw a line through this data point, right? Suppose if I be able to uh, so if the proxy of this data point, let's say it is x1 dash, is x2 dash, and is x3 dash, right? Now if I represent this x1 x2 x3 using this proxies, I can be able to represent this data points using single line, right? Only this line, correct? I do not need the two dimensions to showcase the data points. Is that fine? Currently if you
Scalar
see,
proxy.
yeah, so currently if I'm able to, so this data set actually is in two dimensions, right? But if I can somehow be able to represent this data uh, using single dimensions, what we are going to achieve using this, we can be able to store this data set using the lesser memory. Is that correct?
Yes, sir.
Yeah, so that's what it is, the PCA. And uh, what kind of line I should be using it, right? So that the error will be lesser, that we need to choose from, that we need to see, and that is what the goal of PCA, right? So what is the goal of PCA?
Using dimension.
Huh?
So to store the multi-dimensional data into lower dimensional data so that we can save the memory space, sir,
Right. So
without reducing the information.
correct. So by actually not losing much of the information, right? We wanted to see that if I can be able to reduce the dimensionality of the uh, data set, so that I can be using that data for further, maybe see this data which is reduced in dimensions, right, can be used for the downstream task. Like for example, if I wanted to use it to find out the BMI, right, instead of using the two-dimensional data set, I can be using only single dimensional data set because it is containing most of the information. That is what the case is. And one of the good examples we have seen in the lectures is the Eigenfaces example. Is that fine? Okay, uh, that's fine. So I need to find out whether, first thing, if my data doesn't lie into the lower dimensional subspace, will I be able to use the PCA? Or okay, I'll be able to use PCA, but whether I will be able to reduce the dimension of this data set?
No.
No, right? Because the data has to be uh, lower dimension. Fine, or lying into the lower dimension space. What does that mean, basically? Can anyone of you explain what does that mean? Like, okay, the data is lying into the lower dimensions of space.
D is less than M.
No, no, that is fine. That's mathematically it's fine.
The data lives in the linear subspace of the original dimension.
Okay,
It on that optimal solution case.
So the data has very low features, sir, because the D is very less. The low dimensional features
okay.
are lesser.
Features are less. That's fine. But let us say if
In low
I,
dimension space, basically we have the scalar proxies that are lying.
okay, I'll take the example of it. Let us say, uh, okay, this is what one vector, right? X1, correct? How many dimensional data is this?
Three dimension.
Three dimension. X2 is, so all of these data points, x1, x2, x3, x4, how many dimensional data set is this? Like if I just have this data set, which is, let's say, capital X, which is a set of x1, x2, x3, and x4. So in this data set, each xi is of how many dimensions?
R3.
3, right? Everything, can you see that everything is in 3 dimensions, right? Is that fine? But if you notice it here, right? So you see that each of these third dimensions is of what?
No use.
0, right? So that is a redundant dimension, right? If I
Yes.
wanted to plot this, I can be able to plot this data set using only 2 dimensions, right? Do I need the third
Yes.
dimension in this case? Means it is,
No.
see, inherently that data set is having that dimension, right? But if I don't use it, if I can be able to, because I can see that
So,
all,
sir, so can we say that in a three-dimensional space, these four data are lying on a single plane, on a plane which
yeah,
is in
yeah,
three
so
dimensions?
which is uh, that means all these data points are lying on a plane, right? Which is, that means what, like if I say a plane, that means it's a two-dimensional subspace, right? In a three-dimensional,
Yes, sir.
if
Yes,
you
sir.
remember MLF or linear algebra part of it, if you can understand, see, so that means every data point is in a plane, right? But this plane is a part of what, three dimension
Subspace, yeah, subspace of three
space.
dimensions.
Yeah, so this plane is a subspace. So all data points are actually
Subspaces.
lying on a subspace of that linear space, right? So or of the space. So that means if I can be able to represent this data using only 2 dimensions, that means using a plane, that will be sufficient, right? I'm not actually losing any information if I can represent this data using 2 dimensions. Is that correct? Correct. So that means
Yes, sir.
this data set is actually lying in a lower dimension subspace in a 3D space. Is that correct? And that's what we wanted actually. So in this case, I can be able to represent the data only using the uh, two dimensions, right? So that is what, or in the another example, if you wanted to see, which is like easily you can visualize. Okay, just a minute. So let's say these are all data points are there, x1, x2, x3, x4, x5, like this, right? Or maybe in this side also. So all these data points are here, and let us say all these data points are actually lying on a, sorry, just, is that fine? So in this case, every data point is in 2 dimensions. Is that correct? Is that fine?
Yes, sir.
Yeah.
Yes,
So
yes.
if every data set point here is on like a two-dimensional space, but if you see this pattern, right, all of these are actually lying on a line, right? Is that that means if I can be able to uh, say that, okay, this is the, this point, all these points actually lying into a one-dimensional subspace, right? 1D subspace. Right. So in this case, I don't need 2 dimensions to represent these data points. I can actually be able to uh, uh, represent all these data points using a one dimension.
Scalar.
Yeah, only scalar, right? And that's what it is meant to be. In this case, how this what do you think? So in this case, what are the, let's say, 1, 2, maybe 2, 4. Third data point is, let's say, 3. Uh, 1, 2, 3. Let's say, okay, 2. No,
3, 6.
maybe 3, 6, or yeah, that is just fine, right? So 3, 6, let's say, like this, right? So all these data points are there. They are actually 2 dimensions, but can I be able to represent them by using, let's say, only 1, 2 as one vector, and then I just use the coefficients, which is 1, then I think it is 2, then 3. Is that fine? So now, if I say that this is my, this one is the proxy, right? X1, x2, x3 dash. Let's say these are the proxies or the coefficients basically. And if I have one vector here which represents a line, So that means if I have this kind of structure, I can use it to exploit maybe, or I can be able to use it to say that okay, I can store this data only using one dimensions instead of the two dimensions. And in this case, PCA will help us to find out this representation, right? The common representation which I can be using, so that I'll be reducing the dimensions of this data set, right?
Yes.
I hope this is now getting clear. Fine.
Yes. Yes.
But now, whatever examples we have seen, there ideally we are seeing that they all of the data points are actually lying on the same line or in the same plane, right? But in real world, that is not the case, right? In that case, in real world, the data can be there are certain errors, right? So, for example, this kind of data set you can be able to see, right? Fine. But still, can we see any pattern in this data? So can we represent all these data points using a single line?
Yes, sir.
Yeah, but it is not like exactly the
Yes,
same.
some error will be there.
Yeah, some error will be there, but then what line will you pick, right? So that is the question. So how many lines can pass through this data set, or how many lines you can draw through this? Like I can have this line, I can have this line, I can have the third line, right? So
Infinite number.
I can have infinite lines passing through this data set. But then which line should I pick so that I'll be able to represent this data set in a lower dimension subspace? How to find it out? Find it out that what is the criteria?
Minimum variance.
Error, right? No, minimum error,
Minimum
right?
error. Maximum variance.
Minimum error,
And
Error, right?
maximum
Error,
variance.
right?
variance.
So that means I should pick that line which gives me the minimum error, right? So how to find out the error? That is another question, right? So that is a question. Let's say if I have this line, suppose, right? So how to find out the error?
Give gaps.
So you can have the projections, right? You can have the projections on that line for each of the data point, right? So these are the uh, projections. And projections, when I say projections, what does that mean? What is the angle between the line and that projection? That's 90-degree, right?
90 degree.
Yeah, nice.
Because that is what gives me the minimum distance, right? So when I have the angle as 90-degree, then that is the minimum distance which we will be able to achieve, right? So and then we can find out. So that's the error, right? So let's say here we have E1, E2, E3 like that. So we have the total error here. Then I can pick another line. Let's say this line, right, which is passing through here, and I can just have the projections here also on this line for each of the data point. Here maybe let's say this data like this. Now which line will you pick, the red one or the green one? Maybe the green one, right? Because
Yeah,
if you
green.
can
Green
see
one.
that the errors are lesser for the
Error
green.
is less.
Yeah, but now this we can see visually, and we are humans, right? We are able to see that easily, right? But then again, for us also, if I wanted to find it out, it will not be that easy to correctly identify which is the correct line. So we need to come up with some algorithm. For that, we need to find out. So what kind of algorithms we can use it? This is unconstrained optimization problem, right? We do not have any constraints here. Uh, what what will be the optimization problem here we will be using, or what will be the objective function in this case, to find out the error between this line and the data set, right? And what that error will be
X minus X
for.
transpose W.
So for all
That.
right, we should be having, we have to calculate the error right? Each error of that line and the point, right? Now I'll just remove all of these things, and we will see for suppose this is what the data set looks like. Okay, in this case, what we are assuming, the data is centered, right? What do you mean by data is centered?
To pass
The
through
mean
0,
will
0.
be mean will be
Is 0, 0.
Yeah. So what is 0? The mean is 0, right?
mean. Yes.
Yeah.
Yes.
So mean of all data points is 0. That is what we are saying, that the data is centered. But ideally, that is also so in real life, that is not the case, right? In ideal situation, we are here, but in this case, it is not there. Okay. Let us. Okay. So okay, fine. Now I need. Okay, maybe I'll use like maybe few data points, because then it will not be that messy. One, two, let's say 3, 4, and 5. 5 data points we will see, and we will try to see the visualization of error. Suppose this is my line which is passing through this data points. The error, we said that it should be a projection, right? So okay, first of all, I will just say that it is x1, this is x2, x3, this is x4, and this is x5. Fine. Now this perpendicular. So what will be the projection of this onto the line? Let's say this line is, let's say W. So the projection of x1 onto W is what?
X1 W.
X1 W or
X1
x2?
transpose. X1 transpose.
X1 transpose W of
X1
W.
transpose W will be what? My
Projection.
projection, right?
It's a scalar
And
quantity.
yeah, it's a scalar quantity, right? And what will be the vector on this W?
X1 transpose W bracket
Multiply with W.
W, right? That's my projection vector. So this is my projection vector, right? X1 transpose W is my projection of x1 onto the W, right? And why it is that? Because you know that the projections will be, I think we all have learned that projections, right, in the MLF. If,
Yes.
if you guys have done MLF previously,
Yes.
so that is what my, and x1 transpose W of W uh, is going to be my vector. So basically, this is the projection vector here, right, for x1. And then this is what this quantity is going to be. So let's say this is my actual x1 vector. Let me draw it for x1, and then I'll not draw it for x2 and all. This is my x1 vector, this is my projection vector, and this is what? The error vector, right? Error vector for x1, I'll denote it by e1. So what will be the e1 quantity? So this is a triangle. You can see the triangle, right?
Yes.
And by using the vector addition or subtraction, you know that it is going to be x1 minus x1 transpose W of W. Is that correct? Maybe I'll just draw it separately here. Let us say this is my x1, right? So this x1 vector, right? This perpendicular. This is my x1 transpose W of W, this vector, and then this is my E1 vector. So by vector addition, right, I can find it out that x1 minus x1 transpose W of W is going to be this E1 vector, right? Similarly, for x2, the 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 vector here will be what? X1 x2 transpose W of W, and the error vector will be, so E2 is going to be x2 minus x2 transpose W of W. All right. And what will be the error 3? It is going to be x3 minus x3 transpose W of W. And similarly, I can go on till En. So here, if I actually want what? The summation. So what that summation will be? So in the generalized format, it is going to be I goes from 1 to n. What will be the so it is going to be xi minus
XI
xi
transpose
transpose w of
W W.
w, right? That's going to be my error. And in this case, so this is going to be error, but this is a function of what, xi or w? What is unknown here? Is it xi is unknown or w is unknown?
W.
W is it?
W is unknown, right? Why w is unknown?
Mm.
Because I can have infinite w's here, right? W
Yes.
actually tells me that is the line,
Line.
right? And I have infinite lines, but I need to pick that line. So that means w is a variable, right? W is a variable which is unknown variable, correct? But xi's are the variables? No, right? Because each of xi I know,
Yeah,
because that
given.
data is I'm
Given.
having the data with me, right? So that means it's not a variable, and hence this is a function of, I can safely write this as a function of w, and which is what, summation of I equal to 1 to n xi minus xi transpose w of w. I hope all of you understood this part. Okay. Okay. Then what is my goal now? To minimize the
As the
error.
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 So can I say that in other words, this minimizing this function to find out the w, and
W.
this is going to be my unconstrained optimization problem, or this is the optimization problem which I need to be which I need to solve. Okay, fine. But here there is a catch. I was saying that we wanted to minimize the error. Can I do that? Instead of minimizing only error, I should be minimizing the okay. Before that, I all of you should know that this E1, E2, E3 are vectors or the scalars.
Vectors.
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 Okay. You are able to see, right? This is E1 is a vector, then E2 is a vector. So all of these are the vectors. So instead of minimizing the vector or sum of vectors, what should I do? Minimizing the length of the vector, right? Is that correct?
Yes.
Or I can say that uh, so I so I can minimize either the length of the vector, or so length of the vector will be what, the square root of this quantity, right? Square root of all of this, right? So instead of that, what should I do? I should be minimizing the length square. That is also same, right? So that will be the same problem. Okay, so I'll just write it down, like is going to be length square of xi minus xi transpose w of w. So that's not that is going to be my goal. So this quantity is actually I have written in terms of algebraic format. How should I write it in terms of vector format? It's going to be summation of I equal to 1 to n, right? Length of this is what, xi minus xi transpose w of w. Sorry, just xi minus xi transpose w of w square, right? Because what is this? This quantity is ei, right? The error vector, right? And I am actually taking the length of this. So basically I'm doing it like this: length of each of error, square of it. Is it fine? And that is what my f of w is, and I wanted to minimize this to this format. Okay.
Just a little clarification. Why you take the length scale and then norm scale, sir? Because ideally, sir, we can see that this is the error vector xi minus xi
Mm.
transpose w into w. Why you take L square?
Length square, huh? Why I have taken the length square you're talking about, or what is it? This is L2
So
norm, right? This is L2 norm. L2 is Euclidean norm, right?
Actually, sir, this is a very big confusion with us, sir. What L1 and L2, and we're not able to understand.
Okay, L1, L2 is nothing like very fancy, right? So there is one L1 norm. I don't know. We have encountered it in MLT yet. I think we will encounter it in week 6. But the L1 norm is what? It's the uh, uh, what is it? Maybe absolute value of the vector, right? Or absolute value of the length of the vector. Fine. So that is what my L1 norm is. So basically, that is, let's say if I have x as a vector, right? So when I write x1 of 1, right? Maybe, okay, or it is denoted by like this, and L2 norm is denoted by like this. Fine. So what is the difference between this? Suppose you have a vector x as x1, x2. Okay, I think then that will, is it not the confusion, right? X1, x2, x3 is what? The elements of this. Fine.
Yeah, yeah.
Then what will be my L2 norm is square root of x1 square,
x1
x2
square
square,
plus x2 square plus x3 square.
that is my L2 norm. Fine. What is my L1 norm? So
Absolute
L1 is
value of x1 plus x2 plus x3.
absolute value of x1 plus,
x1 plus
or
x2 plus x3.
is it like this?
Yeah. Yes. Yes.
But absolute value of what, right? So that's what, if you say that, what is the absolute value of x1, x2, x3? So
Or negatives.
sorry. So you
Well,
guys
it
have
means no negative.
yeah. So you guys have not studied this L1 norm previously?
I have not studied, but sir, generally by and large, sir, we are using only L2, sir. Whenever we
Yeah,
see the, yeah,
correct. So basically, what is it? This is so you know what is the distance? So generally, how you calculate the distance? We actually take the Euclidean distance, right? When I call
Yes,
you
sir.
a distance, it is Euclidean distance, but that is not the see. People always think that there is a distance between x1 and x2. So this, let's say these 2 points are there. If I ask you the find out distance, what you do is you
X2
just,
minus x1, root over of x2 minus x1 whole square.
so basically what you do is you use this uh, 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 Pythagoras theorem to find out the distances between these two, right? When I use that Pythagoras theorem, that is your Euclidean distance. But there is who told me that okay, this is the distance I should be using, right? That's not the thing. There are different distances, which is, let's say, Hamming distance. Maybe there are I think Frobenius kind of that distance, right? So there are different distances. So there are scientists who have used different distances, fine. But most commonly used distance formula is what? This Euclidean distance, which is this one, right? That is what, like, most commonly used distance formula. But that's not the only thing to find out the distance, right? So there are different formulas, and that's why these norms are coming out. So this norm is what? Let us say, okay, what will be the values, right? So let us say my vector is like this: 1, 2, minus 3. Fine. Or okay, first of all, I take 1, 2, 3. What will be the distance using L1 norm here? Is 1 plus 2 plus
6.
3, which is 6. And using L2 norm, what will be the distance? It is 1 square plus
13 to
square
13.
plus 3 square, which is square root of 1
Root
plus
14.
4 plus 9, which is root 14, right? And root 14 is how much? Can you just, like, maybe the guess?
3 point something.
People say
3 point something, right? Whatever, like maybe 3.14 or something. I don't know.
3.741.
Yeah, 741, let's say. So this distance is calculated using L1 norm, and this distance is calculated using L2 norm, right? See, when we talk about the two-dimensional data, right, this seems very reasonable, fine. But when it is a higher dimensional data, in that case, that is not the case, right? So that is not the way we should be using it. So there are, whenever it is required, we will use L1. Whenever it is required, we will use L2. In what cases we should be using it, maybe you will get to learn in week 6, right? Why we should I use it or not. But most commonly used norm is L2 norm, and that is what we are using here also in this case, right? So when I'm finding out the distances, this is a L2 norm we are using it. Is that fine? There are other norms also. There is one norm which is L infinity norm, right? I think that that again will come in deep learning case. But right now, you should understand that this is different ways of showcasing the distances, right? Which one you should pick, that is up to you, or that is based on the applications which we are using it, right? Currently in this case, in this PCA, we will be using only L2 norm. Fine. So when I say length of EI square, what does it mean? So suppose each EI is xi, yi, zi. What will be the distance here? Xi square
xi square,
Y square
y square, zi square.
and f square, right? Because this is what this notation, right?
Now,
This norm notation means what? Square root of
uh,
uh, square root of
distance
square of
from the
each of the
distance of the
elements.
point from the origin.
Yeah, or you can say that it is square root of all the elements inside the square, right? I'm taking the square of it. So it actually does not make any difference when I take the square of this norm, or if I just keep it as square root. Fine. So generally it is this is for convenience purpose when we use some calculus, right? So calculus method. So in this case, if I say that what is my f of w, we have seen what is f of w, which is
Summation of
summation of I equal to 1 to n.
x, norm of xi.
Let's say if I just do it like this, fine, and I will use, instead I will use equal to 1 to n. What is each ei? Xi minus xi transpose w of w square. Is that okay? I wanted to minimize this to find out the w, right? I will do one thing. So generally you can take the average of it, and what will be the average of this? I just
1
so
by n.
so what is this? This is what? Average error, right? Is that fine? So if I,
Sir, error projection, original point minus projection must come, no?
this is the projection, right?
Divided by omega transpose, W transpose W.
No, that is so when I use divided by norm of w, that means I am taking the unit length of w, right?
Unit length. Oh,
Yeah. So that is normalized one version, right? So for example, if I just go back to this diagrams,
okay, sir. I understand. Understand.
understand, right? So if I'm
Yeah.
using w, is fine, or I can use the w by w, that is this, right? That this
Normalized vector.
normalized vector, and then I need to multiply by that amount, right? So in that also is fine, that is also not a problem. But right now it's not required here. Whenever it is required, you can use it. It's not a problem, because it's just the that vector I am taking, the unit vector I am taking, then how much distance I should be moving it by, because this is a scalar quantity, right? Xi transpose w is a scalar quantity. Maybe I'll just, if that thing is there, maybe I'll just explain.
Sir,
Yeah. So okay,
sir,
give me a minute. I'll finish this, and then let's say this is my w, and this is w by norm of w. What is this? This is a unit vector.
unit.
This is my x. Suppose. What is this projection here on this w? It is x transpose w, right? Is that correct? This is a scalar quantity, right? So if I wanted to find out this vector, right, xi transpose w, or this point, because this point is a vector basically. So this, how much I should multiply with this so that I can reach it here. So I should be multiplying with All right.
Yes, sir.
So that is because this is a scalar quantity. I'm just multiplying to the uh, unit vector.
That X transpose W, how it is coming? The proxy of X star.
Yeah, this is the projection, right? Uh, so this, okay. So this x is perpendicular to okay, not x is perpendicular. Sorry, this line is perpendicular to W, right? I have you done the MLF course previously?
Yes.
Yeah, so I think we have extensively talked about projections, right? So x is a projection of x, okay, or this point is a projection of x onto W, right? And I know this is perpendicular to the W, right? So this vector, the blue color vector is perpendicular to W. So uh, if any vector is perpendicular to another vector, the dot product of that vector and the other vector is what in that case?
0. Dot product is 0.
0, right? So if I use that method, right, you can actually find it out that this quantity is going to be x transpose W. Okay, I can actually show you how it is coming, but I think see it will be a maybe at the end if you want, right? I'll just tell you, fine, if I get some time. Otherwise, it will be like waste of time because this is what there in the projection. So this is, you need to study projection. Maybe it is there in MLF. You can refer, or else just wait for some time. I'll at the end of this because there is a proof for this, and it's simple proof. It's not like very difficult proof. I will show that proof also to you. Is that fine? For now, just understand that this proxy is coming by using the dot product thing. It's x transpose W is a that is a proxy of
Ac-
x onto W when I, or it's a projection of x onto the W. Okay.
Actually, in the lecture itself, W, like Sir has considered W to be a unit vector itself, basically.
Yeah. So that also is fine. No, I told you, right. It is not
Yeah,
like
yeah.
it is not like a
Not a
same
hard
thing.
and fast rule, but yes, yes.
Yeah. It's better generally if you take the unit vectors.
Unit
It is
vector
better
is
for
better.
calculation. Yeah,
Calculation.
it's better. Yes, yeah, that's it. Like, so here we are taking average error, right? So if you don't take average error, that also is not the problem. You can take average error and you can't take average error. That also is okay. Okay. So let's say if my f of w is equal to let's say w square. This is an unconstrained optimization problem. In this case, can you tell me how can I solve this problem to find out the minimum value of, uh, or if I wanted to find out minima of f of w, to find out w. What is the calculus method we
Differentiate.
know? Differentiate with
Differentiate.
respect to w, right?
With respect to the include
And equate it to 0 to get the minimum value of w. So what is the differentiation? It is 2w equal to 0.
W is close to
Equal to
0.
0 is the value at which
Yes.
this function is minimum, right? That is why we have studied in calculus. So if I have this quantity here, f of w is equal to norm of xi minus xi transpose w of w square, how should I differentiate it, or what will be the differentiation coming out from it? So for that, first of all, I need to understand another linear algebra, which is, let's say, what is the norm of, so how should I write this norm of x square? Any, let's say x is any vector, norm of
X
x square,
transpose X.
x transpose x, can I write it like this,
Yes.
right? And if it is xi, then it is xi
X right
transpose
transpose X.
xi, right? I hope all of you know this. So in this case, what is my this quantity is xi minus vector. What is the vector here? Xi minus xi transpose w of w. So this can be written as summation of xi minus xi transpose w of w. This vector, its transpose, right, into xi minus xi transpose w of w. All right.
No, no, Xi transpose W into W, right? I think.
Right. This one. Okay. Maybe I can just. Uh, Okay, maybe I'll put the brackets here also. Yeah. Okay, that's correct. Right. Uh, let's expand it a little bit. Maybe I'll just write down everything in here, which is, so it is going to be summation of I equal to 1 to n, 1 upon n, and this is my f of w. Fine. So what next? It is 1 upon n, and then uh, okay. Let's say I'll just take another example, which is A transpose B transpose. If A and B are the vectors, in that case, how does it look like?
B transpose A.
B transpose A, right? I hope all of you know this, all of this linear algebra. So in this case, how this expansion will takes place?
In the first expression also you'll have to separate xi transpose omega.
Yes,
First
yes.
one.
Yeah, this one. This is wrong. Yeah, correct. So can you just expand it, and so it will be, I think you can just do it like simply
Xi
also.
minus x norm.
Hmm? Can it be xi transpose here and okay, so maybe I'll just keep it with you, right? So because I think it is all there in the
Sir,
lectures, you can.
yes, sir. It is everything is in lecture. It is
So it's
calculation.
just, yeah. So maybe I'll just not dive into it much. Uh, I will just show you what is the
The
result of it.
end results.
Yeah. So it will be 1 upon n. If I just like do all the calculations, it will be 1 upon n summation of I equal to 1 to n minus xi transpose w, and okay, again, this is a minima problem, right? This is minima for w. Uh, Fine. So now I'm what I'm doing here is I'm just finding out the minimum for this. If I wanted to remove this sign, right, negative sign, then this problem will become what?
Maximum problem.
Maximization.
Maximum problem. Uh, to say transpose w. That's what it is. One more constraint I can put it here, and what that constraint will be. So this is unconstrained optimization problem right now. If I wanted to put another constraint, right, and that constraint will be, let's say, mass of w, 1 upon n xi transpose w, or summation of I equal to 1 to n xi transpose w, and here the constraint is yeah. So if you can solve this problem or this problem, they are both equivalent, right? Majorly this is possible, right? So that is not a very big problem to solve. I hope all of you know how to solve it using the Lagrangian methods. We have seen previously also. You can do that, but we have already the solution for this problem, and that problem, so the solution is w transpose 1 upon n. Uh, Not, this is not a solution. Maybe this is like uh, the simplification of it, and that is going to be summation of I equal to n xi minus for xi into xi transpose w, right? Is it okay? I think okay. There is some problem here. I think the squared quantity is there. Fine. And here we are saying that this is what is my this quantity here. It is what the
Covariance
Had
it is
matrix.
called as a covariance
had in
matrix.
covariance.
So it can be denoted by C, and it is covariance matrix. Do you agree that it's a covariance matrix?
Yes, sir.
Yes, right?
Yes.
What is the covariance between two vectors?
In
So basically, how to find out if you have one vector x and another vector y? Generally, how do you do that? Let's say you have some quantities present over here. What you do is You just or let's say two
Expected
variables
value.
are there. Yeah, that also is there. Or another thing is uh, you just subtract the mean from x, right? The mean of x and mean of y. You take the deviations, and uh, then you take what, like the product of it, right? Product of the deviations, that gives you the covariance between the two variables. If you remember it from the stats.
That
So
will
in
be
this
the
case,
correlation, all right.
correlation, okay, the correlation in that case, right, it is like divided by root of sigmas, right? Sigma x and
Right.
sigma, and the quantity which is present in the numerator, that is what your covariance, right?
Covariance.
Is that fine? Basically it is like this, no, xi minus x bar transpose xi minus xi, right? Xi minus, oh, sorry, no, not xi, yi,
Yi minus
yi minus y
y
bar.
bar.
That is what your and this is actually summing from,
Covariance.
yeah, and that is your covariance,
Contour.
and divided by, if I just divide it by sigma x and sigma y, root of sigma x and sigma y, you will get the correlation. But this is what your covariance is. But in this case, why it is looking like this? Because we are saying that the data is centered, right? So when I say the data is centered, then that means this x bar and y bar is equal to 0,
Zero.
and that's why we can actually write this as xi minus, sorry, xi into yi. All right. And what will be the dimensions of this matrix, the covariance matrix?
D by D.
D cross C, right? I hope this is fine. This is like there is no confusion, right? And then the in this problem, I need to maximize it for w, right? And the constant is w square equal to 1, right? If I solve this, what will be the solution to this problem? W is going to be the eigenvector, right?
Eigenvector. Okay.
Eigenvector of the eigenvector of
X.
C
Covariance
corresponding,
matrix.
yeah, corresponding to highest or largest eigenvalue. Is it okay? So what we are saying here, if I wanted to find that w, right, which gives me the minimum error, right, that line which we are trying to find it out, right? So that was the goal we have seen from the previously, like whatever we have done it for this, right, to find out this w which gives me the minimum error. What is that line now? This line is nothing but the eigenvector of the covariance
Mac.
matrix. In this case, we have seen that we started with what? Reducing the error, right? And we ended up with this equation where we are trying to maximize this quantity. Basically, what you are trying to do is you are trying to maximize the variance, right? Variance between the data points. So if the data or data points, or you can say that the proxies of those data points, if the variance is highest, that same thing means the error is lowest. Is it okay? Okay. So what will be the algorithm here, the PCA algorithm? What do you do in this case, PCA algorithm? If I wanted to write it stepwise, the data is of x1, x2 up to xn. Each of xi is what? D dimensions, right? Assuming that this is centralized or data is centered. If the data is not centered, what to do? How to make the data centered if the data is not
Then
centered?
you have to calculate the mean and
Yeah,
subtract each point from the
correct.
mean.
So what will be the mean of this data set?
x1 plus x2 plus x3 by n.
Yeah, so generalized
All
format is, if I take the sum of all the vectors and divide it by n, that is my mean, right? And what will be now the new data set? That's going to be x1 minus mu,
mu.
x2 minus mu, and up to xn minus. Is that okay? This is what my mean looks right. Or you can say that each of xi here is now equal to xi minus mu for all I. I for all I, which is, let's say, long to I goes from 1 to n. Okay. Now, what is the next step? I will find out its covariance matrix. What is the covariance matrix?
1 upon n x
Combined.
trans.
So let us assume that this is x now. Okay, this is all x's. I'm seeing that this is like, or maybe I can just write it like this: xi minus mu transpose xi minus mu, right? Then what you do next? Find out its
Eigenvector.
eigenvalues. So let's say lambda 1, lambda 2. How many eigenvalues? Okay, what is the uh, dimensions of this covariance matrix? D cross D, right? So how many eigenvalues? Yeah.
This
Yes.
covariance matrix should be 1 by n,
X into X transpose, right?
right?
Sorry.
X
The
into X
covariance,
transpose,
Yeah.
right?
Fine. Fine. Yeah. Yeah. If I use D dimensions, this should be it. Yeah. Correct. This is what the case.
Yeah, in this case, it would be a number on this color.
Yeah. Correct. Correct. It should be x transpose. Okay. In this case, how many I okay, and it is it's a D cross D dimensional matrix. How many eigenvalues it should have? Lambda 1 to lambda n or lambda 1 to lambda d?
Lambda d.
lambda 1 to lambda d.
Lambda d, right? And suppose there is a relation between these eigenvalues like this. So suppose lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3, like that, up to this. In that case, the first principal component will be what?
Lambda
W1.
1, W1.
Yeah, okay. Okay, or I can say that W2, it will have how many W's can have?
D
number.
two.
Is right. And the first principal component will be the eigenvector. So this is eigenvector, right? These are all eigenvectors. First principal component will be W1, which is corresponding to the lambda 1. Is that okay?
Yes.
Nice.
Yes, sir.
I'm taking the first W1, lambda 1, and finding out first its lambda 1, and then make it as W1. Then what happens next? What is the next part?
Sir, I have a question here.
Yes. Yeah. Tell.
Given the W1, how can you find lambda 1?
Given W1, how can you find out lambda 1?
Lambda 1.
Okay. So do you know the eigenequation? Have you studied eigenequation? What is the eigenequation? Let's say if any matrix A is there, the eigenequation is A lambda equals to
Yes.
AW equal to
AW.
A equals to lambda.
lambda W.
Okay. Okay. AW or AX, let's say.
Yeah, AX.
Oh, I'm just taking the okay, in this maybe okay, W also is fine, no issues. In case AW
Lambda
equal to
W.
lambda W, right? So if
Yes.
I know W, if I know A, can I be able to find out lambda from this eigenequation?
Yes. Lambda transpose BW.
Yeah. So this is C. In this case, we are actually finding out the eigenvectors of covariance matrix. So the eigenequation corresponding to this covariance matrix will be CW equal to lambda or let's say lambda 1 W1, right?
Hmm.
And then how to find out lambda 1. If I just wanted to find out lambda 1, if w1 is given to me, is just it is w1 transpose
CW.
cw, right? Correct.
Yes.
And that is actually, that was the equation we actually were getting. If you just see it carefully, right? So this was w transpose cw, and
Yes.
if I just maximize it, right? So maximizing it means like simply its w will be that one which is corresponding to the highest eigenvalue. Okay, fine. So let us try to understand this also now. Fine. So, but this algorithm is not finished yet, right? Because in this case, suppose this was my data set. What we have found out now in the first iteration, this is an iterative algorithm anyway. So let's say this is what my w1, right?
Hmm.
uh, and when this is w1, that means what, like suppose this is e1 error, this is the minimum error, right?
Yes.
E4, E5, and E6. Fine.
Some of these error will be minimum.
Minimum, right? Some of the error is minimum in this case. And now, uh, so when I represent this data set using this W1, what I'll get? That is the question, right? So what will be the representation here? W1, which is in how many dimensions?
D.
D dimensions, right? Correct. In this case, it is 2 dimensions, but in general case, it is 3 dimensions. And what will be its coefficients?
So coefficients, I didn't get your question.
X1 transpose W1, right? Is proxy.
Ah, right. Yes, yes.
Because this proxy, I was actually multiplying with W1, right?
Mhm.
This is X1 transpose. If this is my X1
Yes,
transpose
right, sir.
W1 is my proxy. If I just multiply with W1, I'll get what? This vector?
This factor, yes.
Correct, right? So how many proxies I am getting here? X2 transpose W1
N,
and 2 X2 Xn
Xn,
transpose W1. Is that okay?
yes.
Correct. Now I'm able to achieve the compressive representation here, right? That was the goal we started with. But now the thing is, the error here in this case is what? Error is basically, or let's say these vectors, right? If I just represent this data using only W1, what I'm losing out here?
All the error vectors.
Yeah, all error vectors I'm losing it out, right? So that means, but these errors might be useful, correct? Because they might also have some information in it, right? So these errors might be useful. The But then the question is how to find, or uh, I should be able to find out those errors as well, right? So if I wanted to represent those errors using another line, and that line will be what then? Because if you see that, right, so all of these errors are actually lying perpendicular to w1, and that is obvious, right? Because we are taking the projections, and when I take the projections, all the projections will be perpendicular to w1. Is that correct?
Yes, sir.
That means all these vectors, e1, e2, e3, e4, e5, e6, they are perpendicular to w1, correct? And if they are perpendicular to w1 and w1 is passing through origin, that means if I just draw a perpendicular line which goes from the origin, right, another perpendicular line to w1 is w2.
So why
And
did you mention origin? Because
this
even
is
if
a
it
center
was
data.
not origin,
No, we are assuming that all of this is a center data set.
yeah, okay.
If it is not, we actually are doing the centered one, right? Right now
Yes.
we are just assuming that centered one. So whenever I just explain it, when it goes to origin, that means we are talking about the centered data
Center.
set.
Yes.
Okay. Now if you see that all of these errors will be lying on w2, correct? Because if you just place it, right, you will know that. So previously these vectors x1 transpose w1 w of w1, x2 transpose w2 of w1, sorry, x2 transpose w1 of w1, x3 transpose w1 of w1, they are all lying on w1, right? Yeah, sorry. Fine. So we might lose out on the some information, but fortunately this information is actually lying on w2. But how to find out this w2, right? How to find out this? You just, the simple thing again, you just need to project this data set onto w2, right? This is my e1, this is my e3, this is my e2, this is my e4, right? So like that, if I project all of these data sets on w2, what will be the projections there? Proxies, it's going to be x1 transpose w2 of w2, right? That vector. All of you agree with that?
Yes, sir.
Sir,
Uh,
can you repeat this question?
so what will be this error basically? If I wanted it to represent this error by using w2, what I'll do is I'll just project the x1 onto w2.
Okay.
If I project x1 onto w2, what will be the proxy?
It is x1 transpose w to
w2, right? And similarly, like all these data points, right? So can I say that it is x1 transpose w2 of w2 is similar to my error e1? This e1 is equal to what? X1 transpose w2 of w2. Is that correct? Not understood?
No, sir.
Okay, fine.
No.
Sir, sorry to interrupt you, sir.
Yeah.
Actually, sir, we have a quiz one tomorrow, sir. Sir, if we here in this session, sir, if you summarize the end result and do some, sir, questions, sir, that will be more useful, sir, because we
Yeah,
will
I'll do
get
that.
confused, sir, because
Agreed.
we are getting into a gated steps, sir, and but we will confuse whatever we have already
No, I'll
remembered,
Exactly
sir.
that.
correct. So I'll just finish this one and then I'll directly. So see, if you understand this, right, then you will be able to solve the question. Otherwise, it is.
Yeah.
I don't know.
Yes, sir. We have some idea, sir. You tell the end result, sir, and solve with the question, sir. That will be because, sir, today, sorry, tomorrow, sir, we will be sitting in front of.
Yeah. See,
Yeah.
but no, don't worry about it. So see, once you will understand this part, right, then there is nothing to explain in this. So this is the last leg of it. I'll explain it maybe 10-15 minutes, and after that we'll directly jump to the questions. That's not a problem. Fine. So there is, after this there is no deeper explanations are required. We can solve the questions after this. Okay. Just give me some time. This is the final thing. After that, I will not go into much theoretical details.
Only kernel part, please.
Kernel, I'll just yeah explain it. It's not like that is also not very difficult. That also is easier. But yeah, but see, if you wanted to understand that thing, right, you should be able to understand this. Then only I'm not actually going into very much details into the derivation part of it. But still, you need this. I'm I'm telling you because if you lose out on this, right, that will be a problem. If you don't understand the geometry, I don't think you will be able to solve any questions there.
This class will be up till
9 o'clock, 9:15 will finish it off. Okay. Okay, just I understand your point also, and that is a valid point. Tomorrow is exam, so we shouldn't be delving too much into this details. That is understandable. But just bear with me for like 10 minutes, and then we'll not take all of this. Then you can tell me the questions. I'll solve that for you, and wherever is required, I'll tell you the concepts. Is that okay?
You know better
It's
for
no,
us.
it's okay. That is a the point is also valid. I'm not saying that it's not valid. Okay, but okay, this is x1 point, right? Uh, what is this? This one is the error, right? E1. So
Yes.
okay, I'll just draw two things. This is my w1. is my W2. Let's say these two vectors are there. What is this proxy here? X1 transpose W1.
W.
And if I just multiply it with W1, this is the vector. Okay, right? What is the proxy of X1 onto W2? This one,
X1 and W2.
X1 transpose
X1
W2.
transpose W2.
And if I multiply with W2, what I'll get?
This
I'll
way.
get this vector, right? But this vector is nothing but what? Like, and what is X1? X1 is this part, this vector, right? And I said this is E1. Can I say that E1 is equal to this part?
Yes, sir.
Right. So that means E1 is equal to X1 transpose W2 of
W2. W2.
W2. But E1 we found out by using what? X1 minus X1 transpose W1 of W1. This is what
So
we
can you explain this a bit? Like I'm not trying to control.
see. I think previously we have said no. What is error one? Error is
Yes.
what? X1 minus X1 transpose W of W, right?
Yes.
So is this similar here? Here, okay, sorry, where I went. What is this error here? Just
X1.
look
Yes.
at it. Just look at it.
Understood.
Correct, right? This is X1 minus this vector that gives me E1 vector, right? But
Yes.
that is again similar. That is again equal to what? X1 transpose
X1 transpose W2
of
into W2.
W2. So if I wanted X1 again back, can I say that X1 is equal to X1 transpose W1 of W1 plus X1 transpose W2 of W2? Is that okay?
Yes.
So if I have this vector and if I have this vector, if I take the vector addition of that, I'll get X1, original X1. Correct? So in this case, my data X1 was in 2 dimensions, right? And if I wanted to explain this X1 using W1 and W2, that is going to be this vector plus this vector.
Yes.
But
100% of the information will be retained.
correct. And if I wanted this data, the 2-dimensional data, to represent using single dimensional data, in that case, how much information I'm losing? This much,
Yes.
right? Because that then it is going to be X1 minus X1 transpose W1 of W1, right? So the residue will be this one, right? Is that okay? I hope this is okay. This till this point is not a problem.
Yes,
So
sir.
right. But in real life, we have X1 in how many dimensions?
D.
3 dimensions. So in that case, how many W1 to how many eigenvectors I can have?
WD.
WD.
WD. So each X1 I can represent using what? X1 transpose W1 of W1 plus X2 transpose W2 of W2 up to
D.
WD.
X X1
D.
is not X2, X1 transpose
WD of W.
WD of WD. So, but I'm saying that this X1, right, which was originally in D dimensions, it is lying into a lower dimension subspace. So I don't need all these D dimensions. Instead of that, let's say I need only K dimensions, right, where K is much lesser than
D.
D, right? Sorry. This K. So what I'm doing is I just retain only this one. So I'll represent X1 by using X1 transpose W1 of W1 plus up to X transpose WK of WK, and I'm throwing away the remaining
D
vector,
minus K information.
right? So uh, this K, right? How to choose this K? Uh, that means how much info, how many, what does that mean? Again, I wanted to retain only K eigenvectors, right? I'm not, I don't want the D vectors, like all D eigenvectors. I'll just keep these k eigenvectors. And what is the criteria where to stop? Should I go till it will become 0, right? So what is the error here in this case? Error will be this, right? This is going to be the residue, right? It might not be 0, but it will be like some quantity. But where to stop is the criteria is 90% of it. So when the residue becomes 90% of 95% of this, then I'll choose only that many eigenvectors. I hope you understand this part.
Sir, on basic doubt, sir.
Yeah, tell me.
So when two orthogonal vectors are multiplied, it is becoming 0, no, sir.
Correct.
So x1 transpose of w1, it is actually 0, 0,
No,
0
no,
into w1.
no. Okay, okay. You just see this diagram. Let's say, where is my w1? Let's say this is my w1. Sorry. This is w1, right?
Okay.
And where is my data point? x1.
Yeah.
So let's say this is a vector, w1 vector, right? And what is x1 vector? This one.
Yes, sir. Yes.
What is the angle between these two vectors? Is it 90 degree?
Less than.
So that means if I take a dot product of x1 and w1, will that be 0 or not?
No.
No, right? And let's say this w2, right? What is the angle between w1 and w2?
90.
So
90 degree.
w1 transpose w2 is equal to 0, but not x1 transpose w1 is not equal to 0, right? Because
but you're putting projection of x1 on w1, no, sir.
yeah, so this error
that projection is
yeah,
x1,
so
x1 transpose of.
No, the projection is even, right?
No. What I am asking is x1t multiplied by w1. That is
X1,
projection.
W.
Projection point is there, na?
Yeah.
So that is called x1t of w1. Huh?
This is projection point.
Yes.
This is projection. And what is the projection vector here? Which one? This vector, right?
Okay.
So what is the angle between w1 and this projection vector?
0.
How? Yeah, correct. Sorry, 0, 0. Correct. So will that be equal to 0 then? So if I just x1 transpose w1 of w1,
it is not. It is 0 only.
Transpose of w1, will that be equal to 0 or not? No, right? When it will be 0,
no. What is the value of the quantity in the bracket? x1t of w1.
This one.
Oh, yes.
This one,
no.
right? This
one. No, only one part. x1t of w1.
This is scalar quantity. This is projection.
Quantity.
Yeah, projection. This is a scalar quantity. I'm just multiplying with the vector, so that becomes a vector. Okay. Okay, that confuses. Fine. So just see this one. Okay, I'm just again putting it out for you. Right. So when I projected x1 onto this point, right?
Okay.
This is my x1 transpose w1.
This is only scalar only.
Scalar quantity, yes. And how will I? Okay, I can prove that to also you. So let's say x1 is. Can you tell me any data point? x1 as okay. Let's say it is a third quadrant, right? In that case, it is let's say -1, -2. Okay. Suppose w1 is equal to. You can take any. So if it is 45 degree angle, maybe
4 minus 4
1
minus 4.
1 by root 2 1 by root 2 1 1.
No, simple. Take a simple thing. No? Let's say 1
1 1.
Right?
So better to take unit vector, no?
It's okay. I'm just showing you that this what is this quantity, right? That's okay. So what is x1 transpose w1? -1, -2, and 1.
-3.
So it is -1, -2, this is -3. Correct. So is this a scalar quantity? So if I have any vector taking a transpose with another vector, that will be what? A scalar quantity, right? But I don't want a scalar. I want a vector. And how do I get the vector?
Into W1.
into W1. If I just multiply with W1, then this become a vector. Vector when I say, then that arrow will come in, right? Like
Okay,
this.
sir. Thank you. Okay.
Understand, right? So the angle between E1 error vector and W1 is equal to 90. So then E1 is perpendicular to W1, but not X1 is not perpendicular to W1, right? So if I just wanted to write E1 transpose W1, then this is true. So E1, what is E1? It is X1 minus X1 transpose W1 of W1. If I take transpose of it and if I just multiply this one, then equal to 0. Okay.
What is the residue you are getting?
What is the
Residue.
residue? Is this one, right? Error.
Oh,
In
but
this case.
previously, like you have written, like
So if it is a
exposed.
multidimensional case, so in this case, okay, here also you see that if I just retain W1, what is the residue here?
E1.
E1, right? And that is what? That is equal to X1 transpose W2 of W2, correct?
Yeah, like can you scroll up a bit?
Hmm.
Oh,
So if I have only 2 dimensions, right? Then my residue will be
okay.
X1 minus X1
So
transpose W1 of W1, which is nothing but E1, which is nothing but
yeah, okay. So previously you are written x1 is equal to instead of minus.
yeah, that is correct, right? So I'm just
Yeah, fine, it's fine.
okay. Till now, I think I hope all of you are clear. So if I wanted, so if I, let's say if I have D equal to 50, right? So what does that mean? How many features are having each of these data point is in R50, right?
50,
And how many eigenvalues I can have? Lambda 1, lambda
lambda 50.
50. That too of which matrix?
50 into 1.
Right?
Huh?
Okay, sure.
These are the
Zero 50.
yeah, these are the eigenvalues of this covariance matrix, right? Which is a D cross D. So here in this case, it is a 50 cross 50 matrix. Fine. It will have eigenvectors W1 to W2,
W50.
right? I wanted to, so let us say if I know that this data is lying into lower dimension subspace, which is let's say 5, right? In that case, what I'll do, I just retain W1, W2, W3, W4, and W5. How can I say that? So I'll just, if I use 95% as the threshold, this lambda 1 shows what? The variance along the W1, right? Right? So
Yes.
how this 95% is coming in? It is a ratio of lambda 1 plus lambda 2 plus lambda 3. So maybe I'll just write it like in a compact format, which is equal to summation of I equal to 1 to 5, right? Divided by summation of I equal to 1 to
D.
50. Okay. So what does that mean? My first 5 eigenvectors, right? They contain 95% of the information, right? The remaining are containing lesser information, so I don't need it. See, you wanted to retain maximum of the information. Suppose my lambda 1 is okay. I'll just take something
Lambda
lambda.
1 greater than lambda 2 greater than, sir, largest descending, no?
Yeah. Suppose my data set, the covariance matrix of is of 6 by 6 matrix, and these are the corresponding lambdas, right? Correct. So this is lambda 1, this is lambda 2, this is lambda 3, like this. So if I say that it is 95%, so what does it mean? How much I should pick up for this? Uh, the total is how much? 3 plus 2, 5, 5 plus 6, 6, and 7, right? So divided by 7.
6.8.
So how many I should retain it here? Uh, that I need to check, right? So it is like if I take 6 by 7, how much percentage it is?
8,
82,
6 by 7
80,
is
85,
80.
85.
Right, so that means I need more. Let's say 6.5 by 7,
92.
92. And then next one, if I add is 6.8, then it is 0.97, right? That means uh, uh, how many eigenvalues I should, or how many eigenvectors I should go for?
4.
5.
5, right?
Oh, is it 5 or 8?
Because it's 3 plus 2, 5, 5, 6, 6, 6.5 and 6.8. This is 6.8. Because 6.5 by 7 is coming as 92 and my threshold is 95, then in that case, how many principal components I need? 5. If my threshold is 0.9, then how many I should retain? 4.
Yes,
Right.
sir.
So you understand, right? So how to calculate all of this?
Yes, sir.
Yes, sir.
Okay, good. So now,
इतना इजी क्वेश्चन नहीं आता ना सर.
no, there are few questions previously it was asked, right? So, but see, everything is like similar. If you think that it is not similar, it is. Uh, see, if you understand the concept well, right? There is nothing very difficult about it. Uh, that's what I am actually stressing it on. How you are going to you should, if you understand the geometry of it, right, then there is no problem in solving this. Okay, what is the next thing in this? So covariance matrix, what is the dimensions? You have seen D cross D, right? But let's say if your D is 1000, in that case the computation will be higher, right? And let's say if your number of examples is, let's say if you have only 100 examples, what does that mean? Xi, how this data set will look like in this case? X1, X2 up to X100,
Yeah, D cross.
and each Xi is in 1000 dimensions, right? In this case, the covariance matrix, what is the covariance matrix? In this case, it is 1 by n Xi transpose, right? And you are actually finding out its eigenvalues and then the eigenvectors. But then the size of this matrix C is of what? 1000 cross
1000 plus 1000.
1000. That means, and then you will have to compute the 1000 eigenvalues for this. There is better chance to solve this problem. And what is the better chance? Instead of finding out the eigenvalues of xi transpose, what you can find it out? Xi transpose xi, right?
Sir, is there any chance for eigenvalues repeated?
In which case, yeah, definitely it can be repeated, right? So there is no problem that it cannot be repeated. That is a possibility. So
It
you
can
can,
be repeated.
yeah, that there is no restrictions on that. That's why it
The
is
eigenvector, if it is repeated, eigenvector can be get.
see with the repeated eigenvalues, right? Uh,
Yeah.
you may get the same eigenvector or you may get the different eigenvector.
Yeah.
So if you remember,
Eigenvector will be, yeah. Eigenvector will be reduced, no?
not reduced.
Same eigenvector may be there, no? For two
See,
eigenvalues.
there may be same eigenvector or may not be, right? If you remember
How?
that theorem from, I don't know if you have done MLF or maybe linear algebra, right? With the same with the repeated eigenvalues, there may be same eigenvector or maybe different eigenvector. Do you know the concept of diagonalization?
Yes, sir.
In the diagonalization, what is the condition?
Diagonal elements must be
Different eigenvalues.
Yeah, you should have the actually you should have, if you have, if it is n cross n eigenvector, if you have n cross n matrix, in that case, if the
And
diagonalization is
eigenvalues.
possible only when if you have n different eigenvalues,
Different
or
eigenvalues.
if you have the repeated eigenvalues, the corresponding eigenvector. So that means you should have n independent eigenvectors, right? That was the case, n independent eigenvectors. n independent, if you have n different eigenvalues, you definitely get what? N independent eigenvectors. But if you have the repeated eigenvalues, then it may have the independent eigenvectors or it may not have. And it may not have, this condition occurs only when, if for the repeated eigenvalues, the eigenvector is same, right? That means if you have eigenvalues 2 and 2 and 1, if these are the eigenvectors, you may have the same eigenvector or you may not have. If the same eigenvector you are getting, right, in that case they are not independent, and if they are not independent, in that case you cannot diagonalize,
Diagonal.
right? So that's why in case of PCA, right, this is the condition.
Sir, practice assignment.
Yeah, just give me 2 minutes, we'll finish it off, and I can take the problems. So what is the easiest uh, problem to solve here is, instead of solving the uh, finding out the eigenvalues of covariance matrix, what you do, you find out the eigenvalues of this matrix xi transpose xi, and this matrix is of how many dimensions? 100 cross 100. All right, 100 by 100 matrix will be there. In that case, what will happen to the eigenvalues? So in that case, if lambda 1, lambda 2, 2, how many eigenvalues you will have of covariance matrix?
So 100, right?
1000, right? If my d is equal to 1000 and equal to 100, what then? This is what matrix xi transpose is, this matrix which is n times c. In that case, what are the eigenvalues of this matrix? They are n times. And suppose w1, w2 to w1000, these are the eigenvectors corresponding to lambda 1. Will they be the eigenvectors of this? Yes, right? Because even if you multiply with any constant to the eigenvalues, the equation does not change. Or the vector does not change.
So I
Vector
do
changes. Yes.
this. The covariance matrix Xi X transpose have 1000 lambdas.
Correct. Because your
And
d is equal to 1000, right?
yes, yes.
And if I have xi transpose xi, in that case, how many eigenvalues you will have?
100.
100. But what are those eigenvalues? N lambda 1 and lambda 2 up to n 100, n lambda 100, right? And what we are saying is, the eigenvalues corresponding to this and this, they are same. What about, but still you have 1000 eigenvalues here. How many eigenvalues we are getting by solving this equation or this
100.
matrix? 100. What about the remaining 990 eigenvalues? They are very low, either they are very low or they are 0, right? So basically they should be 0 in this case, uh, and that's why it is good to solve uh, by using this. When this is possible, when this is good to solve uh, this equation, is when your n is much smaller than the d. But what will be the eigenvectors corresponding to this case? If I find out the eigenvalues of xi transpose xi, will the eigenvectors be w1, w2 to w1000 or no? Essentially you will not get w1000, right? 1000, you will not get the 1000 eigenvectors. Instead of that, how many eigenvectors you can get it here? 100.
100.
But they will not be the same as w1, w2 to w1000. They will be beta 1, beta 2 and beta 100, right? But then
Okay, sir.
this is not the because what are the principal components? These are principal components, w1, w2, because principal component, we say that they are the eigenvectors corresponding to the eigenvalues of covariance matrix. This is not a covariance matrix, this is some other matrix. Let's say this is matrix K. We have the eigenvectors corresponding to these eigenvalues as this. But I wanted what? W1, W2, these eigenvectors, right? How to find it out? We can have, there is one term, right? So I think we have that alpha term which is present there, and we have that factor, right? How do you do that? If I just divide it by root of like that, right? I think it is beta 100 by root of n lambda 100. These are what? Equivalent to W1 and W2 to W100. Is it fine?
So in this case, n will be 100, right?
N is going to be 100 in this case, right? I hope you understand this part. Okay, so okay, if you don't also, you can, this is not like very difficult one. You can see that there. I think there is a problem with the students regarding the kernel matrix, right? What is this kernel matrix? And
Sir, I have a doubt in practice assignment, question number 12.
yeah, tell me the question.
So this xi transpose xi is not kernel matrix, right?
This is not kernel matrix. This is similar looking kernel matrix, but this is definitely not the kernel matrix.
Sir, also give one example where there is a numerical where we need to prove whether the kernel matrix is valid or not. That kind of numerical also.
Yeah, I'll tell you how to solve that.
Yes.
But can you
The
tell me
question is very
I will tell you the kernel thing. You just tell me the question. That's the only concept remaining right now.
The only concept.
Huh?
Sir, can you just move up once? Yeah, in this one, sir, I have a query. The one which you have mentioned, beta 1 by root n lambda 1. So this is the this is the corresponding eigenvector for xi transpose xi, right?
No, beta 1 is the I
So
corresponding.
beta 1 is the I correspond.
Beta 1, beta 2, beta 1.
Beta 1, beta 2, beta 1.
Okay, and what about beta 1 by root n lambda 1? That one?
That is going to be the same as
That is
W.
going to be the same as W.
Not
Okay,
W1000,
okay.
W100.
Not W1000, W100.
Okay, so these are basically the eigenvectors of the x into x transpose.
Yes.
Okay,
Yes.
got it.
Yes.
X into x transpose.
So, okay, maybe I'll just
So
raise it.
maybe I'll just raise it.
So,
okay, sir.
Okay, sir.
okay, I am getting that.
Okay, I am getting that.
Yes, sir. The echo is there.
Yeah, and yeah. So, what are, let's say, lambda 1, lambda 2, and let's say if it is d-dimensional and n is the number of data points. In this case, it will have
Lambda d.
d.
Lambda.
N times c is right. In this case, what are the eigenvalues of this? Or maybe I'll just say that the corresponding eigenvectors are W1, W2, and WD. If NC is there, then what are the eigenvalues of this? It's just multiplication.
Multiplication.
Sir, the covariance matrix is x lambda x transpose.
X transpose.
Yeah.
Yeah.
And lambda d, and then you, instead of just finding it out, we know that the eigenvalues of these two matrices will be the same, right? And that too, like not all the eigenvectors. This depends on, this is this, the dimension of this is d cross d.
Dimension of this is d cross d.
So d cross d and cross n. And how many eigenvalues will get it here?
Eigenvalues will get it here.
N lambda n.
The n. And now
And
this is
now
corresponding all
this
of
is
this.
all of
These beta 1, beta 2
these
are,
beta.
okay, I don't know why it is getting it echoed there.
Echo is happening.
Yeah, when he is, I think there is. Are there any two devices you're using? Beta
Or
1,
maybe can you use headset?
No, I am using headset only. There is a, I think from
Yeah, from this side.
beta 1, beta 2 to beta n are the corresponding eigenvectors of n lambda 1, n lambda 2 for this matrix, right? But this is beta 1 is not same as w1, w2, or either wd. Then how to get that is by dividing it by eigenvalues, right? And then they will be equivalent to w1, w2, wd. That is what, not wd, wn, right? Because you have until n dimensions. Okay. The question, somebody was asking me the question. Can you just tell me the question? What is the question?
Sir, I'm not able to because question is very big.
You can.
So it's on the portal practice assignment.
Okay, okay. Just a minute. I'll just open that one. Week 1, 2.
One from
Week 1, practice
question.
1, question number 12. This one? This one, right? Consider the following image.
12th, sir.
Oh, 12th, okay. Consider mean center dataset obtained from the banking domain, that is okay, each of which is described by 7 features. Dataset is represented by this. You can run the PCA and observe the residues vanish completely after K. Little later, a domain expert makes the following observation. If Ci represents the ith column of Xi, X, okay, ith column of X, okay. The set of vectors are linearly independent. The following relations are satisfied. What is the value of K? Okay. Okay. It's easier, right? I don't think it's a problem. Okay. How many data set here looks like? 100 cross 7, right? 100 is what?
Data points, and 7 is the dimension.
Oh, 7 is the dimension. So then it is not 100 cross 7, right? It is 7 cross 100. Usual, how you usually represent this matrix is D cross N, right? So here D is 7 and N is 100. All right. So then it is X of 7 cross 100. This is my data set. Now here we are saying that it is completely, so okay, in that case, first of all, how many K's, how many W's you will get if I, so it is X transpose or X transpose. X is transpose 1 upon X transpose, it's like 1 by 100. Okay, not 1 by 100. What is the dimension of this matrix? This is covariance matrix. Dimensional covariance matrix
7
is
cross 7.
7 cross
7
7.
cross 7.
So how many how many lambdas you will get first of all?
7.
Lambda 1, lambda 2 to lambda 7. So that means how many corresponding eigenvectors you will get?
7.
W7. So when it says that after k iterations, it's going to be the residue is going to vanish, or maybe it is going to be very lesser, or it's going to be completely zero, right? After k iterations. So
Sir,
k's
it's saying
value,
4, right?
huh?
Its value is 4.
Yes, that is correct. That is k is 4. I'm just telling like how it is 4. So the correct answer is 4. There is no doubt about it. But how many you can get 7, right? So what it is saying that uh, it is getting completely vanish after k. What does that mean basically? So I said each of this data point can be represented. How should I represent it using all these eigenvectors? Can you tell me? It is x1 transpose
X1 transpose Omega 1. Oh, sorry, W1, W1.
W1 plus x2 transpose W2 of W2, sorry, x1 plus, and like that, and then it is x1 transpose W7 of W7. So after first iteration, what will be the residue? So the residue will be x1 minus x1 transpose W1 of W1, right? Is the residue?
Yes.
Right? And that is equal to, if I see this equation, let's say this is equation number 1. From 1, I can write this as x1 transpose W2 of W2 plus x1 transpose W3 of W3, and like that up to x1 transpose W7 of W7, right? What is the residue after the second iteration? This x1 minus x1 transpose W1 of W1 minus transpose W2 of W2, and then whatever the remaining quantity is there, it is here. Fine, like that. What it is saying that after k iterations, maybe I do not know what is the k iteration, but suppose it is k equal to 2. What does that mean? The quantity on this side is going to be 0, which is what? X1 transpose W3 of W3. You are understanding? Let's say if it is getting 0 after the first iteration itself, what does that mean? All these data points are lying on W1, right? If all data points lies on W1, what will be the residue after W1?
0.
0, right? That means x1's, let's say this x1 is x2. Okay, maybe I'll just talk about only one point.
Sir, how can we do this question in like the person has done only said 4?
Yeah,
so
that
how
is what.
can we done?
So okay, so you see that the set of vectors are linearly independent. It said, right? Which are linearly independent? C1, C2, C3, and C4. These are the linearly independent set of vectors. C5 is a linear combination of C1 and C3. C6 is a linear combination of this. All of this is written it here, right? In the simple example you see, right? Can I tell you the example here? Is this is W1, this is W2, right? And let us say this is my X1. X1 is lying on W1, or I'll say that. Okay, let us take two data points, say X1 and X2. What is X1? Let's say it is -1, -1. This is my X1, and X2 is, let's say, 2, 2. Is that okay?
Yes, sir.
So what is my matrix? Data matrix? -1, -1, 2, 2. Is that correct?
Okay.
Yes.
Now what they are saying is this is C1 and this is C2. Right? Are C1 and C2 linearly independent?
No.
Yes, no, they are not.
No, right? So if I want to represent this data, do I need these two vectors, or if I just know one vector, I can be able to represent it? So what is the span of this data? Is like only one dimension, right? Or so any vector is sufficient, right? Here
Yes,
to
sir.
represent this data point.
Yes.
Correct, right? So here they are saying that there are C1, C2, C3, and C4. They are linearly independent. Suppose there is one data point X3. Okay, is X3, and suppose it is what is this data point? Can you tell? Can you guess? Okay, maybe I'll just take it in the positive quadrant so that the guess will be easier, right? So suppose it is here. X3 is here. So what is this X3? 2, 3. Is that okay? So what this becomes 2, 3 is my C3. Now can you tell me, is C1 and C2 are independent, linearly independent or not? No.
No.
But C1 and
C3 is not.
linearly independent, right?
Yes, sir.
So if I wanted,
Yes, these are independent.
So if I wanted this data set to be represented by using a line or something like that, how many dimensions at least I need, or
Two
how
dimension.
or how many vectors I need it here?
Two vectors only.
Two vectors are needed, right?
Two vectors. Yes.
So like that, here we have C1, C2, C3, C4. These are linearly independent, and C5, C6, C7 are some combinations of these vectors, right? Linear combinations of these vectors, right? Do you agree this?
Linear combination कौन है sir? C5 और C7?
C5, C6, and C7, right? You can see the linear. This is linear combination, right? C1 plus C3, 2C3 minus C1 and C3 are linearly independent, but C5 is linearly independent.
No, dependent.
No, dependent.
C6 is linearly independent or dependent?
C6, there is C3 and C4. So these
So,
are dependent.
right, and C7?
Dependent.
Dependent.
Always dependent.
Yeah, so that means there are 4 vectors which are independent, and there are 3 vectors which are not linearly, they are dependent. That means if I wanted to represent this data, uh, I don't need all 7 vectors, right? It is sufficient to have only 3 vectors there, right? Oh, sorry, 4 vectors there. I don't need the remaining 3 vectors, right? To have this data set in here.
1 to 7 we have how many independent?
Okay, first place, this matrix is written as like this word, right? 100 cross 7, correct, right? So what does that mean? This data is generally you write x as d cross n, but in this case it is given to me as, so in ideally it should be 7 cross 100. This is like x transpose, which is 7 cross 100. Is that okay? Sorry, 100 cross 7. Correct?
Yes, sir.
So that means this x transpose given here, where are the features? This x1, this x2, no, not x1, x2. Let's say, I don't know.
C1. This is written C1, C2, C3,
Yeah, let's
C4.
say C1, C2 to C7, right? And here it is, each of C1 is of 100 dimensions, right? This is basically 100 cross 7.
Out of which we have calculated, out of which we calculated C5, C6, C7 are linearly dependent.
Dependent. So we have this 4 dimensions, right? These are what? Basically D, right? Out of which,
Yes, sir, I got the answer, na. So 3 to dependent हो ही गए, तो answer तो आएगा 4.
4, and that is the
No
answer.
need for this.
Correct. That is
Answer 13 में.
Which one?
उसी के नीचे वाला question.
Yeah. This one is W is like this. X1 and x2 is this, and this is L, where W is a vector and L is a line perpendicular to W that passes through the origin. Okay, R1 and R2 are the 2 regions on either side of the L. If X is arbitrary vector in the plane, select all the statements. R1, okay, this region is what? Positive. W transpose X is positive. Is where? Or W transpose X, right? Is what? Fine. So W transpose X is greater than 0 is denoted by R1 or R2. Okay. Do you understand?
W trans sir question एक बार समझा दो.
Okay. Okay. Let us see. If this is your x1 and x2, right? Is 2-dimensional. X1, x2 is like axes, right? So 2 dimensions, or maybe you can just write it as like xy. Simple way, right? And if you have line passing through this, right, and you have certain data points here, let's say x1, x2, so like this, so many data points are there. What you are doing here is this your, let's say this is a line passing like this, and this line is perpendicular to this. Let's say this is W. So what is the equation of this line? W transpose, and X is your matrix, data matrix, right? Like it will have x1, x2, like all this x1, x2, x4. So what is this line? W transpose X equal to 0, right? And the region which is here, it is what?
Greater than 0.
W transpose X is greater than 0. So that means any line, if I pass it here, right? Any line which is going from here, it will have, let's say, what is the, maybe this is W transpose X equal to 5. The equation of line is W transpose X equal to 3. Are you understanding this part? And what about this region here? This
W transpose X is equal to 5 कैसे आया वहाँ पे?
No, some imaginary things. It's not like the exactly 5. I'm just saying that it's going to be positive.
Sir, where is the X vector?
X is not a vector. X is what, the matrix here. Okay.
But here W transpose X equal to
This
0.
R1. But is this R1, R2, R3, R4? These are the
regions.
Projections or regions?
Regions. What is that? Let's say in this case, if it is, this is.
So, sir.
Oh, you guys
sir,
have not studied it anywhere. This part.
So, sir, can we say that here W transpose as X equals to 0 है ना? तो वो intercept है, वही कह सकते हैं ना?
Correct. W transpose X is 0 is because it is passing through origin, right?
Projection हो गया ना sir, projection हो गया ना, वो तो W तो वही.
No projection. See, this W transpose X is 0 is the equation of line, right?
Okay, sir.
Okay. You guys have not studied it anywhere, this part. Okay.
Where X lies are here in the graph?
Okay. It's not X actually. This is, let's say, this is point x1 and this is point x2. Okay, I'll take you the simple example. So suppose x1 is equal to, I don't know. I'm just taking some random example.
Some other point.
Some point sample. Let's say 1, 2, right? W1 is a vector which is, let's say, -1, or
-2 and 1. -2 and 1,
-1, right? No,
no, 1, 1, 1, +1, +1.
-2 and 1.
-2 and 1, yeah.
Is that okay? So this is what 1, 2 and W1 is. So if I take X transpose W1, what does that mean basically? It is, or W transpose X1, whatever you want to take, then that means X1 transpose is 1, 2, and this is -2, 1. That's going to be 0.
इसका आंसर कैसे पाएगा? उस क्वेश्चन का आंसर कैसे निकलेगा मतलब?
हाँ, I'll tell you. So do you understand this part first?
Yes, sir, I understood.
Right. So like this, if you have so many data points, right? So the region which is upward of this, right? It's a positive region. Where if I trying to draw a parallel line to this, right? So this line which is there already, which is perpendicular to my vector W, the equation of that line is W transpose X equal to 0. If I that means W transpose X is 0 means this line is actually passing through the origin. If I take any line here, right, which is again perpendicular to W but parallel to this line W transpose X equal to 0, it is going to be W. So the equation of this line is not equal to W transpose equal to 0, or what should be the value in this case? It should be C1, but this C1 should be what? A positive constant. Okay. So anything which is this side of this line W transpose X equal to 0, it's a positive region, which is, and it is denoted by W transpose X is greater than 0, right? So that means that coefficient, the intercept, right, that will be a positive, or you can say that the slope is positive on that side. In this case, in this side region, the equation of that line is W transpose X is less than 0. That's what is that? If I take any line in here, which is W transpose X, the equation should be, let's say, C2, but that C2 is going to be negative intercept, right? So it's going to be, let's say, -1, -2, -3, -5, -10, anything, but everything towards this region, right? The equation is W transpose X is less than 0. So if you just see that my W is here, right? So what do you think, the all the
R1 positive.
R1 is should be W transpose X. So what will be the that region is W transpose X
I
is
think R1 is greater than 0.
0, and for R2 it is
It should be less than 0.
0. And what about L, line L?
Equal to 0.
Because it is perpendicular, right? So W transpose X equal to 0. So what are the options here? This one, and this one.
Sir, I have a doubt.
Yeah.
Sir, intercept sir, वो PPT sir.
Huh?
Intercept में थोड़ा doubt है.
हाँ.
Let's say sir, we have हाँ sir, वही पे PPT में.
हाँ. Okay, here. Okay. What is it?
हाँ सर, लेट्स से वी हैव, मतलब सर अपने पास ये जो लाइन है ना, इंटरसेप्ट ए डब्ल्यू ट्रांसपोर्ट एक्स इक्वल्स टू C2, ठीक है? तो जरूरी नहीं है ना सर कि वो जो इंटरसेप्ट है दोनों का एक्स इंटरसेप्ट और वाई इंटरसेप्ट दोनों सेम हो. अगर सर आप वाई इंटरसेप्ट अलग है और एक्स इंटरसेप्ट अलग है तो सर कौन सा मतलब लेंगे सर?
It's not the intercept here, right? So what is the C1, C2? Are they the scalars or the vectors? Scalars, right?
Scalar.
So it's not exactly the intercept of this line. Okay, the equation of this line is W transpose X. Okay, what is general equation of line? Do you know what is the equation of line? Any line?
Y equals to mx plus c.
Okay, so how do you find it out? Let's say if this is x1 and this is x2, and if any line, suppose it is passing through this, right? And you just say that pi equal to
mx plus c.
Okay, right. So what is m and what is c in this case? What is
C
m?
is the intercept.
What is it?
X direction पे sir.
What is which?
C is the intercept and m.
Do you take this intercept or this intercept?
X direction.
X2 direction, right? And the slope which you take is
yes,
this one, right? Correct.
Yes.
If I go through this, what is the equation of this line?
Y equals to mx 0.
0, right? Or whatever you are just talking about. So it is actually equal to 0. Mx plus 0.
Sir, C is the Y intercept. Huh?
C is the Y intercept. Y in this case, okay. If I actually this is basically I should write is this as not Y equal to mx plus c.
Ax plus by.
X2 equal to
mx1 plus c.
But c is x2 intercept. X1 equal to x2 equal to this is mx plus mx1 plus 0, right? That is the equation of line. Right. So in this case, m is what? W, right? We were talking about this as the weight vector, right, which is actually passing through this, correct? And what is the equation of this line now? This line.
-1 by m. X. -1 by mx.
It is, can I say that
X is plus minus
m 1 by m x1.
-1 by m x1.
Right, no? Is it correct? I think that is not a problem in here, right?
Yes, correct.
But if you have x2, if I just see that is x2, and if this line, right, what is the relation between these two lines? They are perpendicular to each other, right? So how will you write these two lines in terms of so x2 is perpendicular to whatever this line is, right?
So the dot product will be 0.
Which one's dot product? This line,
Don't know.
let's say this is x2 because this is different line, right? Let's say it is x2 prime. What does that mean? It is x2 prime, x2 equal to 0, right? x2 prime transpose x2 equal to 0, right? Right, like
Yes,
this.
sir. Yes, sir.
Correct. That means if this is my x2, then my x2 prime is or x2 prime is this line, right? In that case, they are perpendicular to each other. If this is x2, right, or this is x2, and if I wanted to draw a parallel line in here, right? What is the equation of this line now? Suppose this is x2 prime. Can you say that this line also is perpendicular to the x2?
Yes, sir.
Correct, right?
Hmm.
But what intercept you are taking in here, right? So okay, that is fine. But can you what can you tell about this line and this line?
-1 by m x1 plus some intercept like b or
Plus
anything.
some intercept, right? Yeah, this plus some intercept, right? That
Yes, sir.
intercept is actually coming in here. It's not equal to 0. Then this some intercept is actually because you wanted to counter, right? With respect, because I'm not changing this line, I'm just moving it to this side, but this is going to be negative one, because if I take this, right, you'll and this side also, if I take it somewhere, right, that's going to be that that intercept which you are talking about, right? That will come in here. That is the same thing. So okay, all of this, right, you should be, I thought you should be have learned it before, but it's okay. This is basically linear algebra part. It's not like very difficult thing to understand also. You can go and check later on. Fine. What else is there remaining? Anything in until this concept? PCA?
Sir, kernel.
Kernel, yeah, kernel I'm talking. Before kernel, until this point is fine. Before going into the kernel details.
Sir, can you scroll up?
Hmm.
Or
This is not
the
exactly I'm talking about. Okay, again, don't.
no, no,
I'm not
not this
giving the
one.
examples. I'm just telling where you need to.
Like the above steps in the
Sir.
previous page.
Okay. Here.
This one. Not this one. Um, yeah, you are getting beta 1 by root n lambda 1. What is this?
This, but because beta 1, beta 2, beta n, or what? They are the eigenvectors corresponding to this matrix, right? Xi
Yeah,
transpose Xi.
yeah,
But
eigenvectors of the kernel.
but our principal components. What are the principal components? W1, W2,
Yeah.
to, right? But they are the eigenvectors of this matrix, covariance matrix, right? Or this matrix Xi transpose, right?
Yeah.
This and this is not same, right? W1 and beta 1. But when I
Yeah,
say
beta 1 and W1 are not same.
not same, but what is same in these two matrices, Xi transpose and Xi transpose Xi? The
Data point are same.
eigenvalues are same, right?
Yeah.
Right, but their eigenvectors are not same. We are able to find out the eigenvalues of this matrix. Why we are doing this? Why we are calculating the eigenvalues of this matrix instead of this matrix? Because D is very large, right? Compared to N. So D is much larger than N, right? So computing Xi transpose and then its eigenvalues, it will be computationally heavy. So instead of that, what are you doing? We are calculating we are calculating another matrix Xi transpose Xi, and we are calculating its eigenvalues, because we know the fact that the eigenvalues corresponding to these two matrices are same. The problem occurred where, even though eigenvalues are same, their eigenvectors are not same. Okay, eigenvectors are not same, but eventually what we want the eigenvectors of this matrix, that is w1, w2, and wd. Even if the eigenvalues are not same, but even if the eigenvalues are same, the eigenvectors are not same, but we need some dependency between this w1 and beta 1. And how that is similar? By this. So if I have beta 1 by root of n lambda 1, beta 2 by root of n lambda 2, like that, that is equivalent to w1.
So you are saying these are new eigenvectors? For kernel.
Beta 1 is the new eigenvector, right?
Beta 1 is the new eigenvector of xi transpose xi, right?
Xi. Yes.
Okay.
Yeah.
Okay. Simply, I'll take.
Why are you
Okay.
dividing with
Okay.
root and lambda 1?
Because
That is
that is
for
a factor. Hey, I think you have not studied the lectures. That's what you are asking.
no, sir. Like eigenvectors are beta 1 to beta n, but
Let's say you have.
this beta 1 by you are dividing with the square root of the eigenvalue. So that is for like alpha k. Those are not eigenvectors.
Okay, I'll just tell you. Let's say this is x1, right? Or not x1. That is your matrix X, right? What is the dimension of this matrix?
3 by 2.
3 by 2, right? Okay. What is x6 transpose in this case?
3 cross 3.
It will be 3 cross 3. But can you tell me? Can we just solve this or? Okay, is it okay if I just write 3 cross 3? Whatever the values are there, that's fine, right?
Right.
Or you wanted me? Okay, we can just do it faster. Okay, maybe we'll just solve it, right? What is x6 transpose then? 1, 2, 3. 4, 5, 6. X transpose is 1, 2, 3, 4, 5, 6. What will be the values here? 1
17.
plus
17.
17. Here?
22.
22. There?
27.
27. Here?
22.
12, right?
22.
Oh,
22.
yeah, 22.
29.
29.
29.
36. 36.
36.
27. 45.
Right? This is what your x6 transpose are there. And then what is your x transpose x? Which is 1, 2, 3, 4, 5, 6. Then 1, 2, 1, 2, 3, 4, 5, 6. What is this? 1 plus 4, 5, 5 plus 9,
14. 14.
14. 4 plus 10,
4 plus 10. 14
14
plus
plus
18.
8,
32. 32.
32 is 32 here. And
32.
then 16 plus 25,
77.
44.
77.
77. Does this two matrix same? X6 transpose and X transpose?
No.
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 But what do you think about his eigenvalues? How many
Same only.
eigenvalues? Okay, if it is same, how many eigenvalues does this have? This matrix will have.
3.
How many eigenvalues does this matrix have?
2.
2, right? So only non-zero eigenvalues will be same, right?
Yes.
So if it is having, so that means here one of the eigenvalues is going to be 0, right?
0.
Do you agree? So it is
Yes.
lambda 1, lambda 2 and 0. Here you have lambda 1 and lambda 2. So this lambda 1 and lambda 2, they are equal, right?
Yes.
But the, let's say it is w1, w2 and w3 will be the eigenvectors here. And here you have w1 and w2. Do these three eigenvectors be same?
No.
No. I am just calling this as beta 1 and beta 2. Okay. Right? What is same in here? These non-zero eigenvalues are same, right? But w1, w2, w3 will not be same. Beta 1 and beta, like not same means they are not equal to beta 1 and beta 2. But I wanted, since I'm not actually finding out this, why I'm not going to, okay, solving this for eigenvalues is better than solving this or not? Which one is better? Like,
2 by 2. 2 by 2.
Right? So that means I will solve it for this so that I'll get lambda 1 and lambda 2, which is again same as this. Then I will solve beta 1 and beta 2. But this beta 1 and beta 2 is not equal to w1 and w2. Right? Then how should I say that? Is there any relation between this? Yes, that relation is, I'm saying that beta 1 divided by root of n. Beta 2 by root of n. N lambda 2 and n lambda 1. Okay. What is n here? if it is D cross N matrix, right?
2.
D 3 and 2. So I'm just 2 times lambda 1 and 2 times lambda 2. If I just do it, if I divide
We
it,
will get
they will
W.
become W2 and they will become W1. That is what we are trying to say here, right? So but this is so whatever example you have seen is like the simplest one. In real life, how it is different, like D will be, let's say, 1000 and n equal to 100. So calculating x6 transpose and then finding out its eigenvalues will be cumbersome. In that case, what you do is just
X
calculate
transpose.
x transpose x and find its eigenvalues. The eigenvalues will be how many? 100.
100.
And they will have beta 1, beta 2 to beta 100. What do you do then? Root of n lambda 1 and lambda 2 of 2.
So in this case, basically, in case of x into x transpose, so basically 900 eigenvalues will be 0, right?
0, yes. 0 or very less, like generally.
Okay.
Right? And that means anyway, you can understand this part that without doing any explicit PCA also, right? You can throw away 900 dimensions basically. That also is there, right? That advantage is there. Okay, but fine.
So you are saying beta 1 by square root of n lambda 1 is W1?
Yes, I think there is, so there is some relation, right? You just check it in the lectures. I'm not exactly sure that it is, but I think if I'm not mistaken, right?
Yes, actually it's like alpha k is equal to beta k by square root of n lambda k, which alpha k is the like they're the
The
coefficients
linear
when
yeah,
yeah they're the coefficients when that we get like when we want to express
yeah.
the
That is in
eigenvector as a yeah, when we express eigenvector as a linear combination of data points, we get some coefficients, and
correct.
that coefficients we get
Yeah, yeah, yeah.
like
So,
each
that's what
alpha k is beta k by square root of n lambda k.
correct, correct.
Uh, so those are not W1.
No, not W1. These are some factors, and then you just multiply with that factor, right? And then so, somehow you can actually use it. So I think yes, I think this is alpha 1 and alpha 2, something like that, right? Uh, I do not have exact. Huh?
Yeah, like I'm getting confused. You are saying W1 is equal to beta 1 by square root of
No, no. The essence is like no. Whatever is there in the lectures is the correct one, the correct expression. I'm just giving you the broader perspective. So what actually exactly we are getting it from here is some relation between W1 and beta 1.
Okay. Basically, the relation between the
Because
basically
yeah, finally I wanted to get W1 right from beta 1 somehow. Otherwise, there is no use of this then, right? Then what is the use of
right,
finding
right,
out
right.
the
Okay, got
eigenvalue?
it, got it, got it, got it, got it. So basically, okay,
Hmm?
understood. Of the original matrix, basically.
Correct. Right? Then let's go into the final leg of this, and which is what
Yes, yes.
the kernel one. What is the kernel trick, right? Okay. What now? Until what we have studied, we understood PCA, and what is the use of PCA, or what is the goal of PCA? To dimensionality reduction, right? Uh, to better represent the data using the lower dimensions, right? That is the goal of PCA. But suppose, and till now, whatever we have seen, right? So let's say x1, x2, and or in this case, right? We have seen one problem here. I think maybe I'll just go again back to this. What are this C1, C2 to C7 here? Features, right? C1, C2, C3, C4, C5, C6, C7 are the features, right?
Yes, sir.
Right. You have, in this case, let's say you have 7 features, and what is the relation between these features? Is it linear? Is it a polynomial, quadratic, uh, cubic? What is the relationship? You can see that. So C1, C2, C3, C4 are linearly
Linear.
independent. So all of this is the linear independence, right? Correct.
Yes.
But what if the relation between these features is not linear? For example, let's say C1, C2, C3, C4 C5, C6, and C7. These are the features, right? Let's say these are independent of each other. And C5, I can express it as, let's say, 5 times C1 square plus C2. C6, I can represent it using, let's say, uh, maybe, I don't know, 5 times C2 cube plus C3 square plus C1, like this, right? So what does that mean?
Are this clustered means?
Huh?
Like C1, C2 means, what are the clustered means?
They are independent, I'm saying, right? Or so when we see here, the relation between this C1 and C2, C3, C4, C5, C6, C7 is what? Linear, right? But what if the relation is not linear? In that case, how to solve this problem? Then can we able to, so whatever we have done, right? PCA, what was PCA? Basically, if you have these data points, when we apply PCA, what you used to get? The final thing is what? We get a line, right? Is that correct? So
Yes.
here you have this, let's say x1, x2, these are the features. Okay, instead of x1, x2, I'm just writing it as f1, f2. Fine. If this is feature 1 and this is feature 2, why we are able to find out this line w1? Because f2 and f1, what is the relation between f1 and f2? Linear, right? What does that mean again? That means these data points are actually uh, along one line, right? But what if the data set is not like this? So data set is like this. Let's say f1 and f2 is there, and the data points are actually lying like this. So can we able to find out a best suitable or best fit line in here?
No.
No, right? If even if I try to find it out, then let's say these two lines I can, let's say, find it out. But still, this is the minimum error or no? No, right? Why it is not possible? Because the feature rate here, so basically it is like this, right? F2 is equal to, can I say that it is F1 square plus, let's say maybe some constant, or maybe 0. What does that mean?
Non-linear relationship.
Non-linear relationship, or here it is a quadratic relationship, right? It's a square relationship is here, right? Or suppose if this is the case, f1 and f2 is here.
Sir, but we can have a line which has the least error now.
No, if let's say if it is, if this is a line, right? If I
Okay.
find it out, for this data points, this is going to be the least error. But what about this? The error will
No,
be
for
zero.
overall, we'll calculate for overall points now, but we can have at least
Can you
one
tell me
line.
where it is, where you can just find it out?
No, we can do it mathematically and find, we can have one line. Sir.
Where? I don't know like how you are saying that. So if this is a relationship, where you will get the best fit line? Which one? Which line you will think? Mathematically also, how can you find it out?
That error minimization.
Yeah, if you do error minimization, which line do you think? See, error minimization means also it is a line, right? So any line will be like this only, right? Maybe this one, or like this, right? But any line will be sufficient to capture the data set here.
No.
All right. What about this data points? If I draw any line is what kind of shape is of line? Maybe this line, right? Or maybe this line with different slopes. But are they even if we use the minimum error thing, I'm not able to actually find out the exact relation between f1 and f2, right? The features, because the underlying relation is what? Maybe the quadratic, maybe the polynomial, right? Let's say if you have this kind of data, right? So if this is a data, can I get only a single line which will actually, so what does that mean? This data set is not lying into a lower dimensional subspace, right? For this, because PCA always gives you what? Line, right? and that is only possible when these features, right, f1 and f2, they are linear structures, right? If it is not, if there is some other structure in this, right? So what is in this case, what is the structure? Maybe it is f2 equal to f1 square, right? What about this? It is f1 square plus f2 square equal to 0, right? Is that correct? Not 0 actually, some r square. Yeah, some r square, because it's a circular relationship, right? In this case, what should we do now? Now we can't be able to apply PCA directly over there. Instead of, what you do is, currently this data set is how many dimensions? 2 dimensions.
Sir?
2 dimensions.
Sir, if you don't mind, you have already explained these things. So can you just jump into the algorithm?
Yeah. So in this case, what you need is, you need something different, right? And what something different is possible is, what you should express this data set, right, in a higher dimension space. So currently this is in 2 dimensions. You just go for higher dimensions, maybe 3, 4, 5, or 6, right? Just represent this data using the maybe more than 2 dimensions, and then you apply PCA into that dimensions. Okay, maybe. Okay, just give me 2 minutes. I'll come back. I'll take water and come back. Just a minute. Okay, so
Sir?
yeah.
Like, I have a doubt in eighth question of mock. Like, I have put 0.1 as the answer, but it is giving the range 0.19 to 0.21.
Mock exam, huh?
Yeah, I don't know like how many decimal places I have to put there. It's not mentioned in the question.
Okay.
Can you give?
Where is question number 8?
Yeah. Yeah.
This is your question, right? That's okay.
Yeah.
It's fine. Like, your answer is not matching in here is fine. Like, consider the center
I
data standard process performed. Consider the following ratio. What is the minimum value of theta? What do you think the minimum value should be? 1 by 5, right? 0.2. It's exactly 0.2. There is no, how you calculated this? So variance along the first principal component is what? Lambda 1,
Yeah.
and sum of variances along 5 principal components is lambda 1 plus lambda 2, something like this, right? The minimum value they have asked. So you can think of, okay, how can you think, like, I think, so basically it's a 5-dimensional data set. You can go back to the
1
first
by 5.
1 by 5. Yeah, that is correct. So that means you are having only one component out of the 5 components, that's going to be 1 by 5 basically.
That means all eigenvalues should be equal, right?
All eigenvalues are 1, let's say, and that's going to be your minimum 1, right? So because maximum
Why
is,
not? Why not zero?
see, the first principal component is the component which is having the highest variance, right?
Yeah. Why
So if
can't
I
others?
so if I
Why
have
can't
0,
other eigenvalue be zero?
okay, let's say, okay, what do you think? How many eigenvalues will this data set will have?
At most five.
5, right? If my first eigenvalue is 0, what about the remaining ones? Can they be higher than this or lower than this?
Higher.
No. Lambda 1 is
It will
always,
lesser,
lambda 1 can be
less than or equal to.
right. So if it is 0, that means all are 0. That is not possible, right? And 0 by 0 is indefinite, right? Then there is no point in this. That's not the valid one. Oh, minimum value should be 1, right?
Yeah.
For anything, and then you should have the decreasing ones, right? But if I take the ratio of this, then it will be 1 by 1, which is going to be 1, right? If all my eigenvalues are 1, in that case it is 1 by 5, which is going to be 0.2. Can you just find out any other combination which is possible than this? If you take any lesser value than 1 right here, that's going to increase this ratio. Do you agree? The maximum sum, which is at the denominator, right? It's going to be 5, right? If you try to reduce these values, right, these values, that's going to be anyway decrease the denominator, and that means this ratio is going to be increased. So the minimum ratio possible is 0.2 only. After
Yeah,
that,
sure, got it.
okay. Okay, so where are we? In kernel, right? What do you do then? If the relationship is non-linear, in that case, what you do is you take this data set to the higher dimensions. What does that mean? I'll tell you. I'm not going to show you what is there in the lectures. You can read it there. I'm just trying to visualize this, and then you can, because to understand the concept, right? Suppose this is x1 and this is x2. Fine. How many dimensions are this? 2, right? Okay, I'll just instead of x2, I'm just writing as f1 f2, because we are denoting dimensions by right. uh, can you tell me these data points x1 x2 x3 x4, they are in how many dimensions? They are in 2 dimensions, but
There is no, but
lower dimensions are squares, right? Right. Correct. But if I wanted to represent this data into higher dimensions, what should I do? Let's say if I wanted to represent the same data points using this relation, f1 square is equal to f2, right? And this is what, like, this is x1, this is x2, x3, this is x4. That means x1, if I put it x1, it's the data point in this is going to be uh, x1 square, right? Then x2 square. So let's say this is going to be like this. I have this here, here, and here. Is it fine? Now let us say these are primes, right? So that is x4 prime, x3 prime, x2 prime. This is x1 prime. Is that okay? So what are these x1 prime, x2 prime, x3 prime, and x4 prime? This is a data set which is actually, we found it out using the original data set, which was x1 x2 x3 x4. Now this is into what, higher dimensions or lower dimensions? It's in higher dimension, right? Correct, right?
Yes, sir.
But now the structure has changed, right? Previously, what was the structure of this data set? Linear. x1, x2, x3, x4, this data set, it was having a linear structure, right? Because these all data points were on the one line, correct? Now, this data structure here, is it linear or not linear? It's non-linear,
Non-linear.
or I can say that it's quadratic. Fine. Is that okay? Fine, right? And okay, so that is was the this is the case. So when we are saying that initially the structure is linear, I can actually so what happened here, I have actually gone go from R to R2, right? And how it is possible, how what function we have used to map this, the quadratic function, right? Right. So how we have went from R to R square using some function which is, let's say it is phi. So I can say that phi of x equal to x square. This is the mapping which we have used. Is that okay? Right. So from going from the lower dimensions to higher dimensions. So this is what the kernel mapping it is there, right? So what we are doing here is, we know that if my so but the objective is different here. What is the objective in this case? Let us say if your original data set, right? So in this case your f1 and f2, this data points, the structure is not linear. Okay, sorry. The structure here, is the structure linear? No. So we have a non-linear structure in lower dimensions. What you do is, you take, so how many, what is this dimensions? Here it is R2, right? I will use some mapping function 5 to go from low dimensions to higher dimensions, let's say 6, right? What happened in this case? I will use some function like the previous one, but the thing is, what we are hoping in here is, the structure, initial structure was non-linear in a lower dimension subspace. By applying some function, that is phi, I am actually hoping that there will be a linear structure in higher dimensions. Okay, and now if the structure is linear in, let's say, higher dimensions, what you do there, you apply PCA in which dimension? The higher dimension. Okay, but the the now the differences, what differences it will have, right? So let's say if you have a data set, it was in two features. When we used to apply the PCA previously, and if the data set, let's say if it was linear structure, the covariance matrix dimensions were what? 2 cross 2, right? Right, and then we had like lambda 1 and lambda 2, two eigenvalues, and we have the corresponding w1 and w2, and let's say we retain only w1. That's how you achieve the uh, dimensionality reduction. In this case, what is happening, we are actually uh, increasing the dimensions now, right? So we are going from R2 to, let's say, R6, and what you do there, so what will be the covariance matrix in the enhanced space, the higher dimension space? Cross 6, right? Then we have lambda 1 to lambda 6, and then we have w1, w2, and w6. And suppose we retain this w1 and w2 in higher dimension subspace. So we apply PCA in the higher dimension subspace. This is what we do. But then you might ask, right, how this is now, this is good, right? How this is good? uh, Basically we went from the lower dimensions to first higher dimensions, and then we reduce the dimensions in the higher dimensions. That is what kernel PCA does. But why it is useful? Because and when it is useful, when you do not have the linear structure in the lower dimensional subspace. So what does happen in kernel PCA? You first of all you increase the dimensionality, and then you reduce the dimensions in there, right? So saying it is with this. So do you understand this part? Means like if you understand this relation, what
Yes.
I'm huh? Any doubt?
Sir,
If yes.
yes, doubt, yeah.
Yeah.
Sir, in this one, basically, like in this higher dimension, which is a 6 by 6, because we have established a linear relationship here, right?
Yes.
So in this one, since we are retaining these two eigenvectors, W1 and W2, so will this W1 and W2
can have W3
contribute to 95% to the variance? Hello?
Yes, yes. So I am saying that you can actually, let's say W3 also. Yeah, that's what. The same threshold you can use 95 or 90%. That means, but this is not the same of this, right? So what we are doing here, this was nonlinear structure. Let us say if I go for
Right.
6-dimensional subspace, I don't know if, let's say, can we just try to see in 3 dimensions, let's say. Fine.
Okay.
So suppose you have this 2-dimensional structure where can we say that I can say that this was a structure, fine, correct? Now what I'm saying is
Right.
go to the 3-dimensional subspace, some mapping I'm using, and now this data set is like this 3-dimensional subspace, right? Maybe it is lying into a plane or something in a 3-dimensional subspace, the same data set, by using some mapping. Now I use PCA over here, right? Okay, maybe the data set is like this, something like this, right? See, it's very hard to draw these dimensions, but the idea is, see, ideally what is the good thing? PCA generally reduce the dimensions, right? So I should go from R
Right.
to R, but why it is not
Right.
possible now? Because this is not efficient technique, because the underlying structure between
In our
these relationships, right? It's not the linear one.
non-linear.
So I should first, what I should do now, I should go to R6, and now I can go to R3. So here actually I'm achieving the dimensional reduction in which case in higher dimensions.
From R6, he'll be going back to R2, right, sir?
R2 or R3, or see how where it is giving you that.
Got it. 90%. That threshold, right?
Yeah. So it may be 4 or it may be 5. This is
Understood.
Yeah. Whatever we are actually looking is like the simpler data. This is not going to be the case in the real life. So it may be, let's say you have R100, right? Then you move on to, let's say, R600. So this 100 dimensional data you look into 6 dimensions, 600 dimensions by using some mapping, and then you reduce it to, let's say, R50, right? So now actually basically you're seeing, right? So you are actually going for 50 dimensions, which is the better one. It is, see, let's say it is D. This is capital D, which is higher dimensions, and this is what we have achieved using the PCA.
So basically, the features, these are transformed features, right?
These are the transform features. So some mapping is there. What does that? So I just told you, right? So maybe it can be, let's say, if you have, let's say, these features are there.
Yeah, understood.
F1, F2 are
Got
the
it.
features, right? What is let's say their relationship is like this: F1 square plus F2 square plus 2 F1 F2
Right. Got it.
and 0. Let's say.
It's okay.
Right, no?
Sir, please take one example where it says whether the kernel is valid or not.
Kernel is valid. Okay, for valid kernel, what are the cases? Can you tell me what are the what Mercer's theorem says to you? The kernel matrix should be symmetric,
Symmetric.
right?
And semi-positive definite.
And it should be semi-positive definite. So when it is says kernel matrix is symmetric, what is kernel matrix basically? It is phi of x transpose phi of x, right? Is it same like that, this structure, right? X transpose X. We used to find it out, this lambda n lambda 1 and lambda 2 is this is what phi X transpose phi of X.
Oh, sir, it should be phi of y, no?
No, X only, right? What is Y? X is my data set of, let's say, D cross N. Then fine, right?
Like they both need not be same, no?
No, this is matrix. See, this is matrix. Okay, matrix is like so matrix. How does it? How it will look like? It will look like this. Phi of, let's say, phi of x1 transpose phi of x1, then phi of x1 transpose. Sorry, phi of x1
I of x1
transpose phi of x2.
transpose I of x2.
Yeah, that's fine.
Fine, right? So it is xi xj. So basically,
But in the lecture, it's given phi of y.
yeah, or you can say that it is phi of xi transpose phi of xj should be equal to what? If it is symmetric, then it is phi of,
Jth entry of kernel matrix.
right. If that is satisfied, then you can say that it is going to be the symmetric matrix, right? And for example, let's say, do we have anything in here? Any question? Okay, in this case, right? If this is a valid kernel or not, this is what it is asked, right? So this is kernel function. What it is saying, x1 x2 is equal to this one. So how will you say that it is valid or not, right? What is the relation between, what is kernel mapping here, x1 x2? So any, see, if you need any more information about this, right, maybe we can discuss it later on, because we are limited on time today. I'm not going into very much details. I just wanted to show, like, tell you that what is the visualization, right? X2 square plus x, what is it, x1 cube x2 plus 1. So how can we show that this is going to be the valid kernel? What we said is k of x1 comma x2 should be equal to what? K of x2 comma x1, right? So this is my k of x1 x2. What should I do now? Instead, wherever x2 is there, I should put it as x1, right? And wherever x1 is there, x2. So what will be k of x2 comma x1? That is going to be x1 x2 again, same.
X2 again same.
x1 square x2
x1 square x2 square
Square
here,
x2 square. Here.
X2 cube x1.
X2 cube x1.
this one. So now are these two same?
No.
No, right? So that means it's not a valid kernel, not valid. Okay, right? When it will be valid? So in case of that one is there, right? I think what is the polynomial kernel? Can you? I don't remember exactly. I think it is x1 x2 plus 1 square. I think this is what
Yes,
polynomial
sir.
kernel with degree 2 is there, right?
Yes.
So this is my k of x1 x2 is equal to this, right? Then k of x2 x1 is what?
Same
x2 x1 plus 1 square. Is it going to be the same? Yes, right?
Yes,
You
sir.
can actually expand it and you can verify it, but that is the
This
same.
same.
Or is it anyway? This is looking like the same thing,
The
right?
same thing, sir.
Like this. Or any RBF kernel. What is RBF kernel? I think it is e to the power minus. What is it? Can you just
Norm squared of x minus y by 2
x
sigma square.
x huh?
Norm squared of x minus y.
Okay.
Yeah, x minus. Okay.
By 2 sigma square, right? This is
Yeah.
my kernel function x1 comma x2, right? So how should I check it now? X2 minus x1, which is going to be e to the power minus norm of x2 minus x1 square by 2 sigma square. So do you think that any vector, so x1 minus x2 norm and x2 minus x1, that will be equal?
Yes, sir.
right? So if you
Yes, sir.
take it and then you are actually taking the square of it, so that has to be same. So that's why it is a valid kernel. So these are valid. Why? Because they are symmetric. That's how you should think about it. How to say that whether any matrix is symmetric? Let's say if I have given any kernel matrix, or how should I say that whether
1 to equal to 1, 1 to equal to 3.
so this is semi-positive definite? Okay, I think there is some issue here. 2
It's
2
positive
say
symmetry.
3
2, 3.
5, right? Is this a valid kernel? This kernel matrix,
No, sir.
is it?
This is the matrix.
Yes, it is.
Yes, it is.
Semi-positive, right?
It is right?
It is
Eigenvalue.
not, no, sir.
Eigenvalue.
Okay, how will you check this?
Okay, how will you check this?
We'll take a
But sir,
determinant.
the
We'll take a
first
No,
determinant.
sir, it is not.
It is not.
it is not the sir.
Sorry? Symmetric. It's not symmetric, right? Okay, fine.
Okay.
So,
It has to be 3 1, right? 3 1. Okay, there is some problem now. Okay, yeah. Now this,
Is
Yes.
how will you say that? How will you find it out whether this is valid kernel or not? If kernel matrix is valid or not, you will check its eigenvalues, right? And how will you find out its eigenvalues? You can find out its
You
eigenvalues, or
can
you
find
can
out
check
which eigenvalue, or you can check
determinant is greater than or equal
it
to
is
0,
greater than or equal to 0.
right?
Right?
Positive is negative, right? 4 minus 3. So this is not valid. Do you understand this? What is the condition of semi-positive definite? Do you know the 4 tests? Do you remember? One is eigenvalue test, another is determinant test. I think one is pivot test, and one more is that is like x transpose ax is greater than or equal to 0. That is my semi-positive definite value. Or eigenvalue test is what? Lambda 1 is greater than or equal to 0, lambda 2 is greater than or equal to 0, like this. What about determinant? So a1 should be greater than 0, equal to 0.
2 minus.
A2 minus a1 or some, I don't know. I just don't. Okay, if I for that I need to take the example, right? So do you understand, right?
You know,
Yes,
You
yes.
take the first
Yes, sir.
matrix,
Yes, sir.
right?
yes, yes, yes.
And then you take the second and the third. So if all the determinants are positive, then it's positive or equal to 0, then that's going to be your semi-positive. If let's say if this is minus 1, so anyway this is not valid, you can just reject it initially itself. So do you understand now whether how to check whether this is valid or not?
yes, sir.
Okay, just a minute. I'll stop presenting. Any other doubts you have?
So, in week 4 EM algorithm, if you want.
Okay. What is any problem you have faced? Can you tell me where you are having issues? Any question I need to solve?
Just a minute, sir.
Yeah. Yeah. Is it here anywhere? In practice reduction, any question if you want. So I may not solve this question, but okay, this is there. Here it is there. It's fine. I will tell you the steps how
Yes,
to
sir.
do it.
Uh-huh.
This question is okay.
Yes.
So we wish to fit a GMM with k equal to 2. What does that mean? K equals to 2? Two clusters, right? I
Yes.
wanted two clusters for
Yes.
x point. At the beginning of the tth time stamp, the EM algorithm, the parameters are as follows. What is pi 1 and pi 2?
Probability of the clusters.
Probability of choosing that cluster, right? Pi 1 and pi 2 is there. Mu 1 and mu 2, mu 1, mu 2, and sigma 1, sigma 2 square are the, because these are the clusters, maybe they will be looking like this. So you have this, you have this, and then you have this pi 1, you have this pi 2, it is 0.3 and 0.4, 0.7, sorry, because it's two clusters, because their addition should be 1, and it will have its own mu 1, and this is having its mu 2, mu 1, mu 2, and their corresponding standard deviations. The density of the points given a particular mixture uh, to you for all points, okay, 1 2 3 4, and it is given to me as a, okay, this, what is this? Xi given Zi is what? Zi is what? Cluster indicator, right? So given that Zi equal to 1, that means uh, uh, given that my point belongs to, or given that I have chosen the first cluster, what is the probability that the point x1 belongs to cluster 1, right? That is what it is there. Then zi equal, f of xi given zi equals to 2 is what? Given I have already chosen the cluster as 2, what is the probability of x1 belonging to that cluster? So in this case, if you see the values, what do you think that point belongs to? Cluster 1 or cluster 2? Which is having the higher probability? Cluster 1, right, for 1 point. So what is asked it, what is the value of lambda k I for I equal to 1 and k equal to 2 after the e step? So this is asked for which point? The first data point, right? Correct. And for this thing, right? So, and after the e step, so there are two steps. What is one is e step is what? Expectation step, and m step is the maximization step. In e step, what do you calculate? The lambda i's, right? Correct, right? Do you remember the formula? Okay, maybe I'll just do one thing. Maybe I'll show you slides, and then we'll explain it from there. Where it is in the first or second is there? Huh. Okay, this is what, like, you do. What is this algorithm is? First I'll find out the lambdas and then find out its parameter, right? And then how to find out the lambda? It's modified log likelihood, and then you find out the values of lambda, right? How do you find out lambdas? What is this? This is how you should find it out, right? uh, is there a doubt in the concept, or is there a doubt
No,
in
sir. The only
numerical, right?
numeric.
So how do you find it out in this case? Lambda is equal to probability of xi given zi equal to k into probability of zi equals to k, right? So I'll just write it down here. So lambda I k is equal to probability of xi given that zi equals to k into probability of zi equal to a. This is fine, right? This is okay, because this is your conditional probability divided by what? The sum, right?
Probability of the data.
Right. Right. So yeah. So in this case, what is, in our case it is only 2 points, right? So lambda I k in our case is going to be probability of x1 given zi equal to 1 into probability of zi equal to 1 divided by the total probability, which is probability of x1 given zi equal to 1 into probability of zi equal to 1 plus probability of x2, sorry, not x2, x1, this is for this point, right? Probability of x1 given zi equals to 2 into probability of zi equal to 2. Okay. What is this probability of z equal to 1? It's pi 1, right? What is the probability that the cluster indicator is 1? Is pi 1, right? What about this? This is pi 1, this is pi 2. Do I have the information about these values? Let us find it out in the question, and I think it is there. Okay, there was a question.
So what, like in the E step we calculate this. What do we do in the M step? That is a bit.
You modify, you actually you use that lambda, right?
Right.
And then calculate its parameter. So well, right now you have
Okay, mu k and the pi k, right?
yeah, mu1, mu2, pi1, pi2, sigma1, sigma2, all of that. So initially you already have found out this mu1, mu2, pi1, pi2 from the sigma1, sigma2 from the previous step, right? This is what, like, but then you use it for lambda, and then again by using that lambda we use, why we are doing it? Because of that structure, right? Okay, this structure is somewhere written somewhere. Jensen's inequality we needed, right? Because I think we were not able to find out that logarithm, right?
Right.
Maximizing we are not able to use because there was logarithm inside. So we use the Jensen's inequality. That is generally Jensen's inequality previously we used for the convex functions. Here we are using it for the concave functions. And by using that, we are trying to maximize the likelihood. So this is the lambda k, right, which is the extra parameter, which was not initially in the algorithm. That's why it is the latent variable. So what you do is, in the first step, you find out lambda,
Right.
but from the previous parameters. Hmm? And then find
Right.
out the parameters using this lambda t plus 1, which is we have found it out later. Then that kind of this way the algorithm goes. Okay. And in this case, if you try to solve this question, right, it is very straightforward. We already have these values given to me, right? Now I should be able to. So this is what f of xi given zi equals to 1, f of xi given zi equals to 2. I'll be using this. I think it is 0.02 into 3 divided by plus 0.054 into that is what your lambda, I think, is to 1 1.
So basically, in the M step, we find the modified maximum long likelihood, right? Right. The parameters basically.
Yes. So in the E step, lambda. E step lambda.
Right.
M step all parameters. This parameter includes what? 1 pi 2
Pi.
2 and sigma 1. How to find it out? So whatever the equation you are having, right? Maybe this is function of all thetas. If I want to pi 1 pi 2. Can you just mute this? I think my voice.
Oh, sorry. Yeah.
So f of theta 1, right? So if f of theta is what? It is like the bigger equation. If I wanted to find out pi 1, then I'll be differentiating with respect to pi 1 alone, right? And then equating it to 0. Then for pi 2, differentiate with respect to pi 2, mu 1, mu 2, like that. And I think all the equations we already have derived it here. So lambda k is coming out like this, sigma k. So for fixed lambda, so in the first step you find out lambda, right? Then you fix it, and then this mu k will be lambda k to the power I into xi by this one. These are all the equations are there. All right.
So MML means modified maximum
Modified
likelihood.
maximum likelihood. Yes.
Okay, got it.
Modified is because we introduced that new step lambda, sorry, new variable lambda, which was not there originally in the uh, in our calculations, because generally we don't, this lambda is not any parameter, right? This is latent variable.
Right. We have introduced this one.
Yeah, to solve that equation, because summation of log we can't find out its derivative, right? So then we did it, what we introduced some lambdas inside, so it will be lambda, summation of lambda into that logs, right? So it will be let's say lambda 1 log of x1 plus lambda 2 log of x2 plus lambda 3 log of x3. So that equation, and where what was the constraint there? Lambda 1 plus lambda 2 to lambda, let's say whatever the numbers are there, that should be equal to 1. That is what your Jensen's inequality is there, right? I think we know this. Maybe I'll just tell you like simply. In the convex term, I'll tell you. So you have this, right? If you know, there are 4 for convex functions, right? How to define a convex function? There are 4 definitions. I think one is epigraph of f. Then I think you should be solving.
Got it.
Got it, right? Yeah.
Right. It's okay.
So you have this x1 and x2, these 2 points. You can actually lambda 1 x1 plus lambda 2 x2. I think if I, and this lambda 1 and lambda plus lambda 2, right? And that is equal to 1. This is the constant over this. This is linear combination. Okay, you can just go back and just see, but yeah.
No, it's okay, sir. You can carry on. Yes. No problem.
This is it, right? Okay. This question I think you can solve. Any other? Okay, if you pause the algorithm at this stage and use lambda ki values to do hard clustering, what would be the cluster assignment? Yeah, so you need to find out first this lambda ki's. So I have found out what here, lambda 1 of 1. How to find out lambda 2 1? So in the numerator it will be 2, right? Zi equals to 2, right? So basically this is going to be 0.054 into.
This is 1 minus lambda.
Yeah, that is also fine. Yeah, that's also fine. So this is for lambda 1 and lambda 2 for 0.1. Then you can find it for 0.2, 0.3, 0.4. But I think it is here, it is asked for only 1. So I think you can just easily find it out. In this case,
whichever will be higher.
Yeah. So argmax of this, right? So you just for Z1, how will you do that? All these values are the cluster centers. You remember this, right?
Yes.
So you need to calculate. You first, for first point you should see that if lambda 1 of 1 is greater than lambda 2 of 1. If this is the case, right? Then what will be Z1?
First one.
Yeah. And similarly, you should calculate lambda 1 for lambda 1 of 2 and lambda 2 of 2. If suppose the relationship is like this, then Z2 equal to 2. And then that's how your vector will look like. So 1 1 1 1 or 2 2 2 or 1 1 2 2, whatever. So that's a lot of calculations is there. Okay. Okay, then
Okay.
yeah, shall we stop now?
Yes, sir.
because I think you should also need some time to revise again. So good luck.
Thank you, sir.
Yeah,
Thank you, sir.
we'll do. Bye. Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Yeah, thank you. Bye.
Good night.